অন হয়ে গেছে কিনা, এটা কি একটা আওয়াজ হলো? Yes, let me start. Just a minute. This one is Lecturate. Yes. Let me add before actually. So today, since we have like 4-hour session, so accordingly, I will plan for a certain breaks. Maybe we can take one break a little big in between, or we can plan for 2 small breaks. That is like in 3 halves we will be doing it. Okay. Yes. So let me start. Okay. So where we ended in the last classes, we have seen the quantum circuit representation followed by the quantum algorithms. We started with some basic algorithm called Day-8 algorithm. And we have seen that it is actually giving us certain sort of quantum advantage where instead of 2 number of queries, which was in case of a classical, it is giving only the result or the desired result in the like suitable words in only 1 number of queries. So that is certain kind of a quantum advantage that we can actually see there. Now, the next was what we also like initiated, that was for the Deutsch-Strotze algorithm. So let me only choose one single color for it. Okay. Okay, where it was instead of 1 qubit, which was the case of Deutsch algorithm, here now we want what will happen for an n qubit system. What will happen for an n qubit system? So it was like our f initially, which was 0, 1 product n. It will be 0, 1, which is a single out or single qubit out. So what was the problem statement? That is, the function can be either a constant function for constant for n qubits. The case will be for all the values. Okay, it will be 0. So for example, for n equals to 3, how many, say possible, how many states we will be having? Say 0, 0, 0, 0, 0, 1, 0, 1, 0. Let me just write it down. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are all the 8 possible states which say n equals to 3 number of qubits. So for a constant function, what was the logic? That is, for all the values, it should be equals to either 0 or it will be equals to 1. That was the logic for a constant function. And for a function to be balanced, it should be, how to check whether a function is balanced or not? We will start with checking all the individual values. So maybe f000, what will be the value? Say for example, I'm just directly considering the worst case. Say for f000, I'm getting a 0. Can I tell at this stage, that is I have done one query, just keep on checking with the number of queries. Here I have done only one query. Can I tell whether it's balanced or not? No. Why? Because the definition of balanced was for half of the inputs I should be getting one value, and for half of the other inputs I should be getting a one value, another value, which is a complement of the earlier half, where the condition is I am unable to say that for which input what value I should be getting. That is whether for 000, 010, 110, and 111 I am getting 0, or for vice versa, or for what exactly values, for what values, set of values I'm getting that 0, that I cannot determine, but exactly the number of zeros and ones, that should be exactly equal. That was the definition of a balanced function. So if 000 is equals to 0, then I cannot do anything. So one query is already gone. Say, now 001, it is, say for example, I'm getting another 0. Okay. Then can I now tell anything? Say 010. For that, I am getting another 0. Till now, I cannot tell. Why? Because I have 8 such comparisons that I have to make, or 8 total number of sets that I should be exploring. So 010 is again 0. So one more query is done. And 011, which is, say, for example, 0. That this is also done. So one more query is done. So out of n states, where n is the number of states and small n is the number of qubits, so where n is equals to 8 basically. So 4 queries I already have done. That is n by 2 number of queries I already have made. And even now, I'm unable to say whether that is balanced or constant. But assuming that it can be either balanced or constant, there is no more probability of that, or that is it is completely exhaustive. Either it will be constant or it will be balanced. If I just check one more, say for example, in the worst case, all the initial 4 is done. I now want to check F110 or 100, which is F4. Say for example, here I am getting the value of 1. Now, immediately on this condition, whenever I'm getting this, I can tell that is by exactly with one more query, with 5 total number of queries, I can tell that yes, it is a balanced function, considering that if it is not a constant one, it's a balanced one, right? But here also, if I get a 0, I will tell that since more than half is already covered, so it is a constant function. Since here I am getting a 1, I will call that it is a balanced function. So for classical computation, in worst case, let me just write it down. In classical computation, in worst case, I have to make how many number of queries? That is n by 2 plus 1, or 2 to the power n by 2 plus 1, considering n is the number of qubit, or basically, say for example, n is the total number of combinations. So at least that divided by 2 plus 1 number of combinations I have to check. Okay. These many combinations I have to check. Now today we will be looking into the quantum equivalent of it. Okay. Just give me 1 minute of time. Sorry for the interruption. Just give me 1 minute of time. I'm again coming back. Just a minute. Yes. Yes. Again, I'm just presuming. Yes. Okay. Thank you. So this is what we can see for the classical one. Now the thing is, we will be gradually build up a quantum circuit, see how the state evolution and the oracle design can be done, and see how the Deutsch-Jotza works. Or we will check also that whether, let us check whether it can also, just like Deutsch, is able to give a certain sort of a quantum advantage or not. Okay. Yes. So for that, for the quantum one, uh, say for the this color is very complicated. I don't know why. Yes. Oh, why there is a lag in this thing? Okay. For the quantum one, yes. So for quantum one, let us consider that our input is nothing but a linear combination of a linear. I'm aiming for covering Deutsch-Jotza as well as Grover, and that is so big. Maybe let us. That is why just try to be a little fast. If you're having any doubt, please put it on chat or try to ask at the end. And if it is like very severe that without that your next understanding will not happen, please just let me know that through chat. So input has to be a linear combination of n-qubit computational basis states. Computational basis means whatever we know for the Z basis, right? Okay, so it is kind of that. Say for example, and also you know a few things, that is 0 on Hadamard gives you 0 plus 1 by root 2. We will all be taking these values, and 1 on Hadamard gives you 0 minus 1 by root over of 2. Okay. So under this condition, just also from these two equations, say for example, 1 and 2, I just want to write a bit of generic expression. Can I write if x represents either 0 or 1, can I just write it? That x on Hadamard will give me something like K0, which has no phase associated with it. And this one is, say for example, minus 1 to the power x times K1 by root 2. Yes, you can write it, because if x is equals to 0, then it is K0 plus K1 by root 2. If x equals to 1, it is basically nothing. So this is a more general form of representing the basis state to the Hadamard form of that basis state. Okay. So the oracle for this one, let me draw the oracle with red color. The oracle or the circuit for this Deutsch-Jotza will something look like this. Say UF is the unitary that works with a function. K0, of course, it will be an integer. Without integer, and it will be either in a like a binary thing only. Say 0, 1 or 0, 0, 0, 1, only with that. Okay. So K0 on, now we will be applying, we will be applying some Hadamard, then the output, say for example, it is x0, then another 0, likewise, there will be a set of zeros, and then H, and this one also H. So all those many Hadamard gates I have to apply, right? And another one, so all these things are my input register, okay? All these are input registers. And this is another one, which is a target register. So this on Hadamard, I'll be giving it to register Y. So obviously you understand that this is this thing only for all these values, and this will be K0 minus K1 by root over of 2 for this one, target register. So X, this entire set, and Y is your input to oracle. So this is your oracle, and it should be giving you certain output. So exactly like that, because of the uncomputation or a reversible logic, you have to do this, another Hadamard for measurement, and this one will be Y XOR of effects or addition modulo 2, whatever you call it. So let me assume that this is my phi 1 state. Initially it is psi 0, this is psi 1, this is psi 2, and this one is a psi 3. Psi 3, psi 2, psi 1, all of you know, because this any quantum circuit represents nothing but a time diagram. So if I say psi 1 means what is the state of the quantum at t is equals to 1, similarly likewise. So at t equals to 2, at t equals to 3, only that thing. So also another thing, if you notice, secant 0, that is this thing, tensor product n, what will be the value on Hadamard? That is on all qubits. Now instead of only a single qubit and its superposed form, now we are interested to write it in a general, more general form with respect to more number of qubits, which is like n number of qubits. So this will something look like this. Ket 0 plus ket 1 by root 2, and similarly it will go on till it is like till the nth one superposition is done. Now it means, see, root 2 will happen n number of times. So it is nothing but on denominator it will be root over of 2 to the power n. And this one will be x, and this is nothing but ket x. Whatever be the x that will be getting. Okay, where x is the, let me also write, where x is the n cubic basis states. And there is a sigma, so all these states I will be covering. Okay, that is, for example, for n equals to 2, it will be from this equation, I can directly write it down that it is 1 by root over of 2 square, which is half, times this thing, which is, say, ket 0, 0, ket 0, 1, represent here, kx means the entire basis state. Okay, so it can be 0, 0, 0, 0, 0, anything that you want. So 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. For example, so this is your general representation. This one is your general. There is certain issue with the black color, or why I'm getting this thing, I don't know. Every time I face this thing. This is the general form. Right? So, and also to notice that here x will be equals to, from 0 it will start to 2 to the power of n minus 1. Okay. And if you notice also here, for n equals to 2, it means that 0 to 3, and this is in decimal, but it is actually nothing but 0 to 3 means ket 0 plus ket 1 plus ket 2 plus ket 3, which in binary represents ket 0, 0 plus ket 0, 1 plus ket 1, 0 plus ket 1, 1. So this is the same meaning only. Okay. General form means I'm just explaining the general form itself. So it's ket 0. This is the input register now. Just do have a look. It is not now only a single ket 0. It is a ket 0 tensor product n. That means n times I am taking ket 0. And now I want to apply an Hadamard on that. So basically, simply by expanding each qubit by qubit by qubit and applying Hadamard of them, it looks like ket 0 plus ket 1 by root 2 for the first qubit. This is for the second qubit. This one is for the third qubit, and similarly, this one is for the nth qubit. Right? Okay. Now, from that, just look at the denominator. It is root 2 times n. So it's basically 1 over root 2 power n times. Can I just write it down? It is in this way. If you just multiply, take these two things. If you just multiply, it will be 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 for 2 qubit. So it is what you will be getting. Now, instead of this, I'm just, for simplicity, I'm writing in this way, that sigma x equals to 0 to 2 to the power n minus 1. Since I start with ket 0, or 0, 0, 0, 0, 0 is always your, or our initial configuration. So let us start with that, and we will go till we actually end at the nth qubit, which is the n minus 1th state. Okay, nth qubit means the third one is basically, or the fourth one is basically represented with 1, 1, because we are starting from 0, 0, just like the array index. If an array has a size of 10, then we start with array index A0 to A9. Similarly, here also I am doing it. Okay. So now our input is in this way, and our target input also, remember the target input to Oracle, it was what? It was root over of K0 minus K1 by root 2. Okay. And output was a entangled output. Why? It was Y XOR f of x, which is a entangled output. Because f of x is somewhere entangled with the previous output of the oracle, which is this x. So whatever x you are getting over here, it depends on that, all those values. While I am calculating this, I have to, for every such values, I have to check this thing. That is how we can define the oracle. Okay. Now, so from this point, now let us compute this thing like y XOR fx. So it will be, can I just write it down in this way, that 1 by 2 to the power, for today's class, I would also do one request to all of you. If possible, if you have a pen and a paper, because our today's entire class will be a bit of mathematical and all those things. We are actually constructing the algorithm itself, how it works. So that we want to convert that, how at measurement we are getting our desired result. So all those things we will be deriving. So there is going to be a lot of derivations, a lot of mathematical expressions and equations. So I would request to all of you, if possible, if you have a pen and a paper, just try to do it along with me. Then it will be very easy for all of you. Otherwise, you might be having certain question. Okay. So just for your things. So this thing, how it is coming? Because we have like 2 to the power n by 2, that is the thing, that is root 2 and this thing together. So from that, I'm just writing it, this thing times how your oracle is mapping, that is x. Remember, x now will be mapped to x XOR or x product y XOR f of x. So it will be x equals to 0 to 2 to the power of n minus 1, get x product, what? This f of x, I will be explaining, don't worry, minus f of x bar, where it means that your 0 XOR fx is basically f of x, and 1 XOR f of x is basically f bar of x. And how we are getting this thing? We are getting it because we have a k0 minus k1 thing. Okay. So if f of x is equals to basically 0 or 1, then fx minus fx bar, that is represented by 0 minus 1, or in vice versa case, it is 1 minus 0. 0 minus 1 means all these things. Okay, so vice versa. So similarly, for that, now let me just rewrite it now in this way, that 1 by 2 to the power n plus 1 by 2 times this thing, sigma x equals to 0 to 2 to the power n minus 1, get x product minus 1 to the power f of x. Okay, minus 1 to the power f of x. Now check if it can be 0 or 1. Based on that symbol I'm just writing, times k0 minus k1. Of course, I can write it down because either it will be like based on f0, fx equals to 0 or fx equals to 1. It will be 0 minus 1 or 1 minus 0. So likewise, so ultimately it's nothing but fx minus of fx bar. So we can write it this way. So this particular equation, okay, now, so what does this represent? This is a phase factor because of a minus 1, this thing. And if you notice, this is independent of x. So only dependent on x thing is here. So this part is independent of your x. Okay. Now from this equation, can I just rewrite it in bit this way, that all the dependent factors of x I will be keeping together, and the independent factor, that is k0 minus k1, I will be keeping outside, and the 2 to the power n I will be considering with the dependent part of x, and only, or 2 to the power n by 2, that is root over of 2 to the power n, I will be considering with the dependent part of x, and root over 2 I will be considering with the independent part of x, which is this one. So in that way, just after a bit of like rearrangement or rewriting, I will be writing it in this way. That is 1 by root over of 2 to the power n, which is 2 to the power n by 2 times sigma was your x equals to 0 to x equals to 0 to 2 to the power n minus 1, then minus 1 to the power f of x times x. This was your dependent factor. I have clubbed it together. So let me put now a product times ket0 minus ket1 by root over of 2. This root over of 2 to this thing, like 2 to the power n plus 1 by 2 is nothing but 2 to the power n by 2 into 2 to the power half. 2 to the power half means nothing but root 2. So this root 2 now I am taking with this part, which is a, say, let me write, it's a dependent on x. And this part is basically independent on x. Independent of x, say. And how I'm getting this thing? This is just an alternative representation. Why here we keep on representing or keep on like changing our notations or rewrite it so that we can get our desired results. Often in one form, it is very difficult to interpret that what will be the next step if I apply certain operator, because whenever it's like a more number of qubits and the general representation of the number of qubits, then it's a bit difficult. So that is why we will be keeping on changing it, where both the meanings are same, but our like operation will be bit easier for the subsequent steps. So alternative representation of earlier equations, say. Okay, so now I am applying a Hadamard on this thing. Hadamard on this. If you check the circuit, it works like that. So if I apply it, it will be, say, now say if my x of I, ket x of I, this thing, ket of x, is on Hadamard, what it will be? Ket 0, the general form that we got earlier, where we got it here. Okay, not here. Basically here we got the general one. So ket0 plus minus 1 to the power x times ket1 by root 2. So if I just keep on applying here, so it will be ket0 plus minus 1 to the power xi, because I have taken I as an indices. So xi times 1 divided by root over of 2. So it will be 1 by root 2 times, means 1 by root 2, I'm just keeping it outside, times sigma ki is equals to 0 to 1. Now see, I'm writing it in a different way. Ki equals to 0 to 1 minus 1 to the power xi ki, and this is a bitwise OR operation or XOR operation, because both are same only. So xi ki times ket ki. Okay, and I am claiming that these two equations are exactly equivalent. For example, let me give you a small example with a small say a particular value so that you understand it. Say for example, I have x0 ket of x0. On Hadamard, it will be in the alternate form. Let me just trust the alternate form. Let me write it down. So it will be 1 by root over of 2 ki is equals to basically it is, I guess, 0 only. So 0 to 0. So it will be no sigma will be applied, or basically it's I equal to 0 to 0. And then it will become that minus 1 to the power x, let me just write xi ki into this thing, that is k0. Oh, general expression is this thing. Oh, sorry, it will be from 0 to 1 only. Yes, I have to write it. So it will be ki here. So in the next line, it will be 1 by root 2 times. Now, can I write it in this way? That is minus 1 to the power, say x0 k0 times k0 plus minus 1 to the power x1 k1 times k1. I can write it down by expanding the equation. So now it will become, let me do all the computation here only. So 1 by root 2. Now, say minus 1 to the power x0 dot 0, because k0 can be k0 equals to 0 to 1. So x0 dot 0 times k0 plus minus 1 to the power x0 dot 1 times this ket 1. So which is nothing but 1 by root 2. Now anything to the power 0 is basically 1. So 1 by root 2 ket 0 plus minus 1 to the power what? X0. That is minus 1 to the power x0 times ket 1. Now is this equation and this equation exactly same? It is exactly same if you just replace the I with 0. So these two equations are exactly same. Okay, so this equation and this equation are exactly same. And why we have taken this form, we will understand whenever we will proceed with the next steps. So since here we have like a lot of equations, and if you're having any difficulty, anyone is having any difficulty to understand a particular step, please let me know. Or if it is like you are having no doubt, that also just try to inform me that if it is okay, then I will understand that okay, we can actually proceed to the next steps. Okay, so till this part, what I have done is after this, on applying Hadamard, I have done one thing, that is what will happen in the if I write a xi in this form. So this form we have checked already, we can do it. So initially we had only ket 0 and ket 1. And what will happen if I apply Hadamard on individually ket 0 and ket 1? Then we have taken a general one, xi. We have seen that xi on Hadamard will give me ket 0 plus minus 1 to the power xi times ket 1 by whole divided by root over of 2. Now what I have done is from this step I have written it in an alternative form of a bitwise OR. Okay, and also for that I have given a proof kind of thing that yes, so both the equations are absolutely equivalent. Okay, so that was our claim. Until this part we are actually here now. Now say I can write my x as xn minus 1. It's just one of the binary values. Xn minus 2, likewise say x1, x0. Okay, and ket x on Hadamard, that is n times Hadamard, will give me 1 by 2 to the power n by 2 or root over of 2 to the power n, whatever you write it, into this sigma kn minus 1 is equals to 0 to 1. Then kn minus 2 is equals to 0 to 1. Likewise, k1 is equals to 0 to 1, and then k0 is equals to 0 to 1. All these things times, I just want to write that minus 1 to the power sigma xi ki, which was in earlier case we have seen that thing, minus 1 to the power xi ki. Now for these many terms individually, instead of it was xi, right now I want to apply it on the entire register. So all these xi's I have taken first, that is xn minus 1, 2x minus n minus 2, likewise till x0. So for that I am here applying a sigma xi ki times that k0, which is now kn minus 1, kn minus 2, likewise k1, k0. Okay, and if you note here that one phase factor comes from each of the factor. So for note, say for example, note that one phase factor means a plus or minus phase factor comes from each of the factors. Okay, so this in very like a bit of composed representation can be written in this way: 2 to the power n by 2, then k means all these things now. Okay, it's not a particular ki, it's all the k's, then minus 1 to the power x dot k times this k. Say this is your equation number 2. Okay, and this particular one was your equation number 1. Which one? It's this one. Let me just mark it. And this is your equation number 1. And this one is your equation number 2. Okay. Now, from this, and k is nothing but this thing, n minus 1 to k0. This is the meaning of this get k. And x dot k is nothing but the sum of bitwise product. Sum of bitwise product. That is x0 k0 plus x1 k1 plus x2. That's a sum of the bitwise AND operation. Sorry, I told it was OR. It's a sum of bitwise AND or kind of x0 k0 plus x1 k1 plus x2 k2. Likewise, it will be till x n minus 1 k n minus 1. All those things. So both are having the same meaning, similar meaning. Now we will combine one and two both, and we'll see what will happen to the output. So now by combining both equation number 1 as well as equation number 2, what we can get is the output. Okay, the output is something like, say, 1 by 2 to the power of n times the sigma. Just do the equation once. If you are having a like note of it, you should be having a detailed understanding whatever I have. So I'm just combining both of them, putting all of them together. So 1 by 2 to the power n times sigma x equals to 0 to 2 to the power n minus 1, k equal to 0 to 2 to the power n minus 1, then minus 1 to the power f of x into, so from one expression I got minus 1 to the power f of x, and from another expression I got minus 1 to the power x dot k times k get k, and in this entire thing tensor product of the second term. Since here also it is independent of x, so I have not done anything with this part. So this is what we are getting. So this is the final output that we are getting by representing both of them, both of the equations together. Now say from this thing, say, if you remember Deutsch, we had got a particular expression of the quantum circuit. Now what we applied there for Deutsch, we applied two cases individually. First, we considered that what if the fx is equals to constant. So based on that properties of fx we will be applying in this equation and see how the result becomes or behaves like. And then we will again and check that after measurement, what was the state of the resistors and all those things. Again, in the generic expression, we will now apply the rules of fx equals to balanced. And what if fx equals to balanced? All that consequences now we will think of applying into this input, we will put as input to this output expression and try to like analyze its behavior. Then post that, during measurement, we'll see that how its value in the registers, all those things like literally change, or how many number of queries it is required. All those things we'll check later. Okay, so that was the thing. After having a certain equation, which is a very generic form, now we will apply a specific cases. That's it. That is how these algorithms are built. So now say my first case, say f of x is constant. So then in this case, a constant phase factor will come out. Will definitely come out of this. Come out of what? Which expression? This thing, that minus 1 to the power f of x. And we will be left with only which factor? That is minus 1 to the power x dot k. This factor. So see here, the phase factor will have equal number of positive as well as negative terms because of minus 1 to the power x dot k. So by expanding it, you can like easily get that thing. So it will be having an equal number of zeros and equal number of positive and negative terms. So this will be cancelled out, excepting the case where your k will be having exact value 0. Okay. So the phase factor will contain, say, equal number of positive and negative terms because of this thing, because we have this minus 1 to the power x dot k, and except for the value when k is equals to 0. So all the other factors, so the remaining factors will get cancelled out. Just see it once for the balanced one. Okay. Just see it for the balanced one from this expression. So that means the first register will be having, that means the first register on Hadamard will be having nothing but this thing on application of Hadamard. Now say that I will explain it, we'll be understanding it, because both the things are almost like a complementary. So let me explain it for balanced. So say for example, now say if x is balanced. I will explain. If x is balanced. I'm just doing it right now for balanced. So for balanced, what we want is, we want to find out the coefficient that is coming out with k equals to 0. So what we want? We want to find the coefficient, say, with respect to, or coming out, say for example, with k equals to, with my k is equals to 0. This is what I want. So for balanced function, the coefficient of k equal to 0 will be what? Of k is equals to 0 will be this sigma x equals to 0 to 2 to the power n minus 1, from where we are getting, from this expression. I'm just writing it. Okay. Sigma x equals to, only the coefficient I'm writing, x equals to 0 to 2 to the power n minus 1, then minus 1 to the power f of x. Okay. Now this is what I want to check. Okay. Now this will be 0. Why? Because this x dot k is equals to 0. So I got this thing. How I'm getting this thing? Say minus 1 to the power, let me just expand it. Minus 1 to the power f of 0 plus minus 1 to the power f of 1 plus minus 1 to the power f of 2. Likewise, till minus 1 to the power f of 2 to the power n minus 1. Okay. Now, since f0, f1, all these things all have values either 0 or 1, right? So it has value either 0 or 1. Why? It's a balanced one also. And since it is balanced, the number of zeros and ones, they are also exactly equal, right? So what value will be, what I might not know. Maybe I do not know what is f0, whether that is 0 or 1. But what is my f2, whether that is 0 or 1. But once I have something like that, this form, okay, I have deduced it. And now f0, f1, f2 till f to the power n minus 1, half of those values, half of any of the combinations is either 0 or 1. So what will happen? This entire thing, whatever it is, the entire expression, that will boil down to 0. And why we are getting it? Because say half of the values out of values from, say, let me write in set form, say set f0 to f of 2 to the power n minus 1, half of the values are 0 and remaining half, again, which value I do not know, remaining half values are 1. So that means minus 1 to the power 0, one value will be 1, minus 1, and minus 1 to the power 1, it will be like minus 1 to the power 0 will be basically this 1, and minus 1 to the power 1 will be minus 1. So likewise, maybe it's like a 1 minus 1 plus 1 minus 1 plus 1 minus 1, likewise. So all the values will be cancelled out. Okay. So if my first register measures a 0, then it is a constant function. But if my second register, now what is happening with the second register? See, in the first register, I'm left out with only 0, the k 0. But in second register, except this coefficient of k equals to 0, what will happen for the other values? For other values, this thing will have a certain of a, I do not know what exactly it will be, but some value which is not exactly 0, but it will be definitely having some value. Whereas in case of constant one, it was like only the k0 was left out. But in case of a balanced one, just try to expand similarly for constant as well. Just try to apply the logic that how the values of f0, f1, f2, f3 and your x dot k, the sum of the bitwise product, that will work. But here what we are doing, we have values from k equals to 0 to 2 to the power n minus 1. But only for k equal to 0, we are getting a 0. But what will happen for k equals to 1? It will be having some value which I do not know, but definitely that means the entire values is not getting cancelled out. So we will be left with a certain value which is unknown to us. So from this expression, we can conclude that if my first register, say first register on Hadamard, if it gives me a k 0, maybe like this, it's not a single qubit, it's a multi-qubit thing, then it is a constant function. And how to check for balanced? For balanced, for k equals to 0, it's 0. But for k equals to 1, 2 to the power n minus 1, all those values are some value, which is kind of a like garbage value or any value, random value. But at least can we say, because we are not here to obtain the exact value of them, but can we say that if it is not exactly a pure state of n qubits, then it will be a balanced function? Because our task is just to identify that whether it's a constant one or a balanced one. And again, I'm just writing it is the case because, let me write, for k equals to 1 to 2 to the power n minus 1, we will get some non-zero values. Yes, some non-zero entries, which will not be cancelled out. So because of that, we are claiming that with respect to only one single query, we can here calculate for Deutsch-Jotzer, we can calculate that whether any input function is a balanced or a constant one, just like in Deutsch. We had done it again in one query. So for both the cases, Deutsch and Deutsch-Jotzer, it takes only one query. But rather, for a classical one, for Deutsch takes two number of queries, but this DJ algorithm or Deutsch-Jotzer algorithm, this basically takes order of n, which is, to be very precise, n by 2 plus 1 number of queries in worst case. Definitely, you can claim that probabilistically, maybe somewhere before n by 2 plus 1 number of query, we can get the output, but that is a probabilistic output. But in worst case, we always consider. So in worst case, it can take n by 2 plus 1 number of queries. So here is our end of discussion of like DJ algorithm or Deutsch algorithm. Right? So how many algorithms we have done? Deutsch and DJ or Deutsch-Jotzer. We will see a bit of Bernstein-Vazirani as well. Bernstein-Vazirani. And post that, we will see at Grover. Okay. So Bernstein-Vazirani problem. Next is this. you might have a question that why we are particularly learning a few set of algorithms, because first of all, there exist a very few set of algorithms, so we do not have much of the options left. And second is, these are very fundamental quantum algorithms that were built, and they all are built with a kind of a say crisis followed by a solution. Let us see how, in how many queries it is able to do. For quantum, for classical, definitely it's something more than that. So all these algorithms are very at the like of that foundational level algorithm for quantum, which may not have a like extremely high kind of a throughput or very high efficiency or very good speed up they are offering, but definitely they are very good in terms of understanding that how the quantum advantage can be thought of, and how Deutsch is expanded or extended to Deutsch-Jotzer, and how some idea of Deutsch-Jotzer is extended to Bernstein-Vazirani. Now, Bernstein-Vazirani also has an extension, which because of the some lack of time we are unable to cover, which is Simon's algorithm. So that would be my request to all of you to go through Simon's algorithm and try to understand or like uncode the quantum circuit. That would be my ask to all of you. But because of the time thing, we are restricting to these three basic algorithms. And one very like kind of a what to say, like a brilliant quantum algorithm where you can see a significant speed up, or it's a milestone quantum algorithm, you can say, that we will cover, which is a Grover algorithm. So like BV algorithm or Bernstein-Vazirani algorithm, it's kind of a Deutsch-Jotzer has a trivial extension, kind of, okay, has a trivial extension in this Bernstein-Vazirani. Okay, so what is the problem statement? Let us see that first. So given an n-qubit input string, where x is nothing but x n minus 1, x n minus 2, x1, x0. And now the thing is, we have to find an unknown string. We have to find an unknown string. Unknown string such that, let me again write it in this way, such that your f of x is basically a dot x, and a is not, the unknown string is say a, and get a can be written as a n minus 1, a n minus 2, then a1, a0. This thing. That is, you have a particular n-qubit input string, which is ktex. That can be anything. Now you want to find another secret string. It is also known as a secret string finding problem. So you have to find another unknown secret string A such that it follows this particular logic. That is fx equals to a dot x, where a dot x is basically the same thing, like xn minus 1 into an minus 1. So all those things. So a dot x is nothing but this thing, a n minus 1 into xn minus 1 plus a n minus 2 into xn minus 2 plus likewise a1 into x1 plus a0 into x0. Okay. And this is a modulo 2. So mod 2. Because it can ultimately be having values zeros and ones. Okay, so if you see here, it is a special case of or special kind of variant of DJ algorithm, along with just with a simple modification that here f of x is equals to a dot x. Initially, it was a condition of a balanced and a constant function, but right now it's a fx equals to a dot x. Okay, so first let me write the general circuit for it. So in classical, in order to do that, how many queries I can check with it? So maybe classical search. So say classical search. Sorry, I'm just writing research. classical search, it takes how many number of queries? Say, for example, initially I have something like this. Okay. This is your xn minus 1, and ultimately, likewise, this can be 0, 1, 0, 0 till 0. Similarly, 0, 0, 1 till 0, likewise, 0, 0, all 0, and finally 1. So this is xn minus 2. Likewise, this one is x0. So in classical one, in worst case, maximum how many number of these particular thing might be required? We might, for this case, we might need maximum number of n number of queries, because every position, it can be either a 0 or a 1. So likewise, we have to check for all the positions, and wherever we are getting value, accordingly, we can tell that this is the case. But in case of quantum, now we will be proceeding with the circuit. Okay. So again, I'm telling, say for example, say secret keys is basically 10010. So in determining that, in worst case, at least how many queries you have to find? Say it's like a 10010. So for each position you have to check, and then you have to, like, for depending on the bit positions, those many queries you have to make. So for classical computation, that is at every position you have to check whether that's a 0 or 1, 0 or 1, 0 or 1. Likewise, you have to check. So classical computation, you need basically n number of queries for a n bit string. So if it is a 5-bit string, you need 5 number of queries. But in quantum, again, the claim is, so it's basically 5 queries, and for n bit string, it's basically how many queries? We go of n, that is n number of queries. This number of queries. But quantum claim is what? That I can solve it in terms of only one query. Okay, so that we will look at. So for that, and also if you see here, for quantum also claims that it's not only one query, also it is not a function of the length of the bit string. So it is independent of that one. If I have a 5-bit string length, then also it's one query. If I have a like 50 or any number of bit string, it is always a single number of query that is required. So first, for this, let me just go through an example first, based on how it works. Then what will be at the end, we will look into what is the quantum circuit for that. Say we have, for example, we have n is equals to 3. That means how many total possible number of states I can have? I can have total number of states as, say, 0, 0, 0 till 0, 0, 1, likewise till 1, 1, 1. Okay. And Hadamard on these 0, 0, 0 will give what? Will give all the ones, that is 1 by root over of 8 times state 0, 0, 0 to 1, 1, 1. Which is nothing but all the 1, likewise. Or say in this way also you can write 1, 1, 1, 1, then 1, 1, 1, 1, transpose, something like that. Okay, say for example, my secret string that I want to find, the secret string is s equals to 0, 1, 1. This I want to find. This is the secret string that I want to have as an output. What is BV problem? The Bernstein-Vazirani problem is, I will be having a certain number of inputs. In this slide, should be xn minus 1. Yes, definitely. This can be anything, like for any given string, whatever you consider it, the alternate one, you have to find it out. Okay, now let us see. So initially, let me start in a fresh one. So initially, say your phi 0 is nothing but phi 0 ket is your ket 0, 0, 0. your oracle is something like that, if it has an x, it will map it through a certain function to -1 to the power s into x times get x. Okay, and if you also see the one of the alternate representation in Deutsch-Jotza, we used a similar kind of expression in that alternate form, in form of -1 to the power k dot x. So often these are certain things that we do for simplicity. Okay. So now my phi 2, that is after a certain time. So since it is like almost an extension, I'll write the quantum circuit letter. I hope you are able to map through that how the oracle, what is the input that is going into the oracle, and what do I mean by phi 1, what do I mean by phi 0 and phi 2, all those things. You should be able to understand. Okay. Now, phi 2 will be 1 by root over of 8, which is a superposed one. So I'm directly taking the superposed one, which is from the ket x coming. So ket x, that means x is the state of all superposed states. Set of all 8 superposed states. Okay, so that means x can be either 0, 0, 0, or it can be 0, 0, 1. Likewise, till it can be till 1, 1, 1. So I'll be putting this thing in this expression, and I will get it like, for example, and what is my s? What was my secret string? That was what I considered like 0, 1, 1, I guess. Right? So I considered a 0, 1, 1. So s is 0, 1, 1, and x can be anything. Once it can like initially it can be 0, 0, 0, or it can be 0, 0, 1, but my s is fixed. Likewise, if I expand it, it will look like something this. That's -1 to the power. Let me write another line. Say s is 0, 1, 1, and this is x, x. Then you will understand it even better. So now I will apply the ktex thing. So it's -1 to the power 0, 1, 1 product 0, 0, 0, ket 0, 0, 0 plus -1 to the power say 0, 1, 1, then 0, 0, 1, ket 0, 0, 1 plus -1 to the power 0, 1, 1, then 0, 1, 1, 0, 1, 0, sorry, then ket 0, 1, 0 plus -1 to the power 0, 1, 1, 0, 1, 1, ket 0, 1, 1 plus likewise, let me just write all the steps. Sorry, it was fixed. Sorry. So 0, 1, 1 dot 1, 0, 0 to the power 0, 1, 1, 1, 0, 1, 1, 0, 1 plus -1 to the power 0, 1, 1 into 1, 1, 0 into ket 1, 1, 0 plus -1 to the power 0, 1, 1 into 1, 1, 1 and ket 1, 1, 1. This is my entire x function. See the superposition. At every step, you should also just keep in mind everything that we learned earlier. So this is the essence of superposition. This is the essence of oracle. This is the essence of quantum parallelism. You can see the real parallelism in front of you. One such combination, why it is giving you one number of query? Because all these possibilities, you are actually calculating in one step. Right. So either it is a perfect match for 0, 0, 0, your secret string, or it can be a perfect match for your 0, 1, 0, 0, 1, or it can be a perfect match for your 0, 1, 0. But if you do it like linearly, it will take more number of time. But if you do it parallelly, then of course it will be taking very less amount of time. Simple. And also, if you just calculate, let me take any one value and let me show you that how to calculate this thing, 0, 1, 1 dot 1, 1, 1 or anything. So 0, 1, 1 dot 1, 1, 1 means 0 into 1, this thing, okay, then 1 into, sorry, 1 into 1, that is not coming, sorry, 1 into this one, and say this one, and this one. Yes, okay, okay. So likewise, I'm just writing. So it's 0 into 1, plus 0 into 1 plus 1 into 1, 1 into 1 plus 1 into 1. All these things mod 2. Okay, so this is 0, this is 1, this is 1. So it is basically what? 2, and 2 mod 2 is nothing but your 0. So all of these minus 1 to the power s into x will add nothing but a certain phases. So similarly, if you compute all the values like 0, 1 to the power this thing, starting from this, all the values if you calculate, which I'm not doing to save some of the time, if you calculate, you will be getting either it's a minus 1 to the power 0 or minus 1 to the power 1. For example, for this case, definitely you can see that you will be getting a minus, say for example, for the second one. Say 0 into 0 is 0, then 1 into 0 is 0, then 1 into 1 is 1. So wherever you are getting 1 instead of a final result 0, there it will be minus 1 to the power 1, which is minus ket 0, 0, 1. Similarly, for the first one, you will be getting minus 1 to the power 0, which is plus 0, ket 0, 0, 0. So ultimately, on each of the basis state, just before that, certain phase factor will be added. So let me just write it down. So it means that all these minus 1 to the power s dot x will add nothing but certain phase factors. Phase factor means plus or a minus. So after calculating from the earlier expression, so just by putting the values or solving each values and putting in expression, we get what? We are getting 1 over root over of 8 times ket 0, 0, 0 plus, minus 0, 0, 1 minus 0, 1, 0 plus 0, 1, 1 plus 1, 0, 0 minus 1, 0, 1 minus 1, 1, 0 plus 1, 1, 1. This entire thing we will be given. Okay. So now, again, I will be doing what? What is my target? My oracle computation is done. Till this part, my oracle computation is done. This is the end of oracle, you can say. But now again, I have to do certain measurement. वो logic था कि measurement के लिए we have to do a certain sort of tuning so that we get our desired result in the way we want to visualize it or we want to obtain. So for that thing, again here we will be doing a certain kind of a rewriting. So rewriting the expressions, we will get this, say 1 by root over of 8, just follow. It's a normal thing. So ket 0 product, very simple algebraic simplification. Ket 0, 0 minus 0, 1 minus 1, 0 plus 1, 1 and plus ket 1 product certain 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. This entire thing. So it will be 1 by root over of 8 times, you can write it down in this way, ket 0 plus ket 1 product, this entire thing, which is this thing, right? Ket 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. Now again, from this thing, let me take ket 0 as common, ket 0, then it is ket 0, then it's ket 0 minus ket 1. And it will be a minus ket 1 if I take as common. It will be another ket 0 minus ket 1 from third and fourth expression. So it will be ket 0 minus ket 1. I hope all of you are able to follow what I'm talking. Because of linearity. Not linearity, these are normal like equivalent expressions. Why we are doing it? So that we can like slowly converge to the like easy visualization of our output. That is what we are aiming for. You will see it. You will see it. So it's 1 by root over of 8 times what it is. This is again ket 0 plus ket 1 product, this thing which is the ket 0 minus ket 1 the factorization, no, that is what here I'm doing, nothing quantum. So K0 minus K1, because once we have the end of oracle, quantum is gone. We are doing other things on quantum, but we are doing simple like algebraic simplifications, nothing else. So K0 plus K1 times K0 minus K1 times K0 minus K1. So from this, can I just write it in this way from this expression, last expression? Can I just write in this way? That is, if I just put this my root over of 8 with all the three terms and make it root 2, root 2, root 2, can I just write it in this way that it is K0 plus K1 by root 2 product K0 minus K1 by root 2 product K0 minus K1 by root over of 2. Now this is first, this is second, this is third. Let me apply individually Hadamard on all of them. So on application of Hadamard, what will happen? So it's age of, yes, so it's age of this thing followed by age of this K0 minus K1 by root over of 2 followed by Hadamard K0 minus K1 by root over of 2. So it will be nothing but my K0. This is my K1, this is my K1, which is also 0, 1, 1. I can write it. And if you notice, this was your, what it was? It was your secret string that you tried to obtain. Okay. And in how many queries quantum is giving you? Only in one query, because measurement I'm doing only once for quantum. But definitely, let me put a pause here and let us just try to analyze or try to think a bit more. So far we can see all these results. But if you very carefully notice that for a particular secret string, if this problem is given to me, then how to know that I have to make it like a s dot x thing, or this is how my oracle needs to be built. How to know that one? Is there any logic behind it? The easy answer is no. That is the logic that you have to put in. Second, also remember, also just like look into the solution. My secret string itself is being propagated very beautifully through the oracle. But we are here just to show oracle. For oracle, the secret string itself is like a black box. It does not, or it does not know that what values it is getting, and accordingly it is doing any tuning. It is not doing anything. So that is why oracle is also known as a black box. So whatever be your secret string, but your logic for secret string problem will be like this. Now see, in that way, knew the code. Oracle knew the code. Yes, you can tell that. So Oracle knew the logic basically that this way, this is the quantum algorithm. This way it can work. Okay. And if you change it, how say for example now, I have given you another secret string which you have to find maybe for a 4-qubit system. Now I do not know what it is. Say for example, I have given key I want this is the perfect secret string. I have to choose one. Say I have chosen 1010. If I give to you, how accordingly, how for this particular 1010, you will be getting the solution, or how to build the oracle in that particular scenario? How to do that? First of all, you have to consider a 4-qubit state. So how many total number of quantum states should be there? 2 to the power of 4, that is 16. So like in this step, whatever we have done here, so sorry, where is it? Yes. So in this step, it will now look like, say, 1 by root over of 16, or you can equivalently write it down as 1 by 4. Then within third bracket, it is minus 1 to the power 1010.0000 get 0000 plus 1 minus 1 to the power 1010.0001 get 0001. Likewise, all the 16 steps you have to write it down, then just do all the calculations based on the same logic, then you will find it. So in that way, you can actually expand it. So that is a scalability, but this is a uniqueness of the algorithm, that you have to know how you have to process the oracle. So these are the few areas where novelty you have to put. And another one very important point here is that Why? After I have this thing, see, this expression is not really very interpretable or readable format. It does not signify much of the things. Few of the quantum states are having a plus and a minus, but how to interpret it? Okay, for our purpose, for our particular problem statement, we have to then do a certain sort of redesigning it. After redesigning, then we apply the Hadamard, then we will be getting the desired solution. Okay, so this is your Bernstein-Vazirani. You will be knowing it. Of course, you will be knowing. But it's just that uh, what are you talking about? Say, for example, I have an array, and now I am telling that I want to search in that array, I want to search the element 50. Now, of course, I have to give it like the general algorithm. I have to first build that, okay, that if say a of I is equals to I10, then do this. Otherwise, just again, just increment, do an increment operator, just increase your index to the next position and then do the checking. That is the algorithm. But definitely what item you want to search, that has to be with you. That has to be with you. So that is a secret string, but that for Oracle, it is unknown. That is what I'm telling. If I do not give you that, please just do it for 1010, you cannot do that. But what I'm telling is, it will not be different for 1010 versus 1001. It is independent of what string you are giving. But definitely as an user, you have to give it, otherwise how you will be interpreting the result. This is not do it. What some result you will be getting. Some A's you have to put, right? Otherwise, how you can devise it? So those things need to be hard coded. But for Oracle, it is the Oracle function is kind of a black box. That is the logic. The algorithm which has that Oracle, that is a kind of a like mystery to it. For Oracle, it's a mystery. That is what I'm talking about. Okay, so I have to keep all the annotations. Just a minute. Where is the? Yes. I'll remove these things, I guess, if they are here. Okay. Yes, so it's 3:25. You want some break now? Let me know. Great, great. Okay. Let's take some minutes of break, say 2 to 3 minutes only. So from say 3, we will give another break. Okay, around at say 4:40 or 4:45. At that time, we will be giving 5 minutes of break because we have classes today till 6. So that is why. Let us now take a break, and again at around after 1.5 hour, we will be taking another break. Okay, so we will start it say from 3:30 or 3:31, 32, something around that. Okay.
Ma'am?
Yes, sir.
Yeah, I'll just make one announcement and for that time, because we are trying to schedule a sample quiz. If somebody wants to take it, he can do it, right? So
Okay.
we'll give that. So, and then of course the quiz will be open till tomorrow 1 o'clock. So you take a break, ma'am. I'll just instruct the participants.
Sure, sir. Okay.
Yeah, sure. Dear participants, we are sending you a quiz, a sample quiz. The sample quiz will be available till tomorrow 1 o'clock. But any time that you start answering the quiz will be closed 30 minutes after you start answering the quiz, right? So at 3:25 or something, you will get the quiz will go. Mail. Mail has been sent, so you will receive a Canvas link. Login. And if you very simple 5 questions, general questions, only 1 question on quantum. So just for trying to understand, please remember that there are multiple answers which are correct. More than one answers are correct, right? So you don't look for most closest answer. If there are 2-3 answers, you can try to do that. Am I clear? Are you able to hear me? Can you just respond on chat? You already gone to the quiz, is it? Yeah, we have mailed you. Please, or otherwise, please log into Canvas. Quick on quiz. Log into Canvas. एक बार आपका स्टूडेंट वाला करके शो कर दो. 3:20. View as the quiz will start at 3:30. So the schedule is 3:30. We thought ma'am will give a break at 3:30. So you can look at that. You can answer anytime. It is open till tomorrow 1 o'clock. Right? Anytime you start, but the moment you start, the quiz will be for 30 minutes. Only 5 questions. दिखा दो, शेयर करो एक बार. Look, view ऐसा रहेगा. Yeah, the Canvas view will be like this. Okay. This is the student view. So you will see the quizzes, and if you click on quiz, it will show you the quiz is logged, of course, till 3:30. And 3:30 you can start attempting the quiz. It will be over in 5 minutes, so no problem. So hope you are able to log in and see the sample quiz, March 8th, 2025 at 3:30 p.m. So we will also know how many are able to log in, and if there are any issues, as I've already mentioned, please email fdp.academy@mnit.ac.in. Mr. Deepesh will write this thing on the chat of WebEx, right? He will put the email ID. You can mail us. We will try to address those issues in the daytime tomorrow. fdp.academy@mnit.ac.in. Yeah, it will come at 3:30. It will be visible at 3:30 under the quizzes. Under the quiz, it will show that it is not open yet. But at 3:30, the quiz will be open. When the quiz will be open, we will show you the student view, how it will be. You can see it on the screen and then go and attempt the exam. I am also logging as student. If you click on it, it will show the assignment is logged. It will be unlogged at 3:30, 15:30. It will show. And if you click on quizzes, it will show sample quiz March 08, 2025. This you can start anytime till tomorrow 1 o'clock, so don't worry. But if you want to just check, you can do that. Yeah, it is posted on mail only. Canvas will send the mail. वो mail भी देखो यार. The mail will look something like this. मेरे पास आया होगा नहीं. हाँ. हो गया आ रहा है मेरे को बोल रहा है. हाँ. This is how it will look like. On the right hand side, you are able to see that sample quiz, and click on quizzes, go to sample quiz, click on sample quiz. There is some instructions, and after that, take the quiz. So once you click on take the quiz, after 30 minutes, the link will be closed. Okay, whatever answers you have attempted, you will be taking. There is a timer which is running, so you can see how much time is left. Tomorrow, when you're writing the exam, you can look at that, right? And when you see the answers, there are only 5 questions here. You can click on the question and go to that question, and you can see the time which is running. 29 minutes 38 seconds is there now. And then when you go down, you can see the questions, and multiple answers may be correct. So please click on, you can select multiple answers. If one of them you feel is wrong, you don't select them, right? So maybe 1 or 2 or 3 or all 4 may be correct, right? So please look at that. One question at a time you will be able to answer, right? So once you select and then you select next means these answers will be marked as thing, right? Like that you answer the quiz. Hopefully this part is clear. So आप कंप्लीट कर दिए, आप भी पूरा कर दो, हाँ कर नोट कर लो, हाँ हाँ ओके ओके ठीक है, गुड, हाँ हो गया, no issues. Logged into canvas while the quiz is on. Will other tabs close? No, मैं भी ले लेता हूँ quiz. The results are shown like this. You can see here. So first question we have attempted. So only IIT Kanpur was not involved, but I selected IIT Kanpur also. So it is showing one answer wrong out of 4. Right, so it is showing the mark is showing as 3 are correct, so you are getting 0.67 points out of 1 is wrong, right? And when you go to the second question, I wrote Sri Narendra Modi, so it is wrong, so I am getting 0 points. Next, I am chairman of AICT, I have answered correctly, I get 1 point, right? So like that, here I answered all 4 are there, so all 4 means correct, so that is 1. Yeah, okay, all the best. So I hope there is not much of an issue. If there anybody having an issue, please know how to know which is wrong, that we will give the key. After tomorrow's exam, we will give the key. You will only know the correct answers that you have marked. Right? You will know your score, but the correct answers we will issue later. Yeah. So thank you so much. Over to Nivedita ma'am. This quiz will be open till tomorrow 1 o'clock. So this is how the questions will be. Multiple answers will be correct. So please check that. Maybe none of the answers may be also be correct. So please, it all depends on Nivedita ma'am. So yeah, over to Miss Nivedita. Yeah, thank you ma'am. Uh, uh, Nivedita ma'am, we can start. Ma'am, welcome back. Can we start?
Sir, just 2 more minutes. I'm just having lunch. Just 2 more minutes, sir.
Sure, sure, sure. Okay.
I'll start. Yes,
Yeah.
yes.
We will take a break for 2 more minutes. We'll start a little later. Yeah, thank you.
It was lecture 8. Where is it? Just a minute. Closed. Just give me a minute. Okay. Yes. Okay. Okay. So now we will see, instead of here, let me just delete these slides. So next, we will enter into Grover. So first, let us see what is the problem statement. Okay, and what is the classical solution. Then slowly we'll enter into the quantum formulation of it. So firstly, let me make it in the full screen mode. Yes. So basically, a search problem or a search algorithm is an algorithm which involves finding out a particular item from a database. These are all the primitive things. So basically, if you have a certain input and a certain key elements, so if your algorithm is able to find that or find the particular say key, then it will return the index where the key element is found. For example, just consider a linear search on an array, and otherwise it will enter that not found or successful, unsuccessful, or some -1, whatever you want to return. So the classical search algorithms are mostly, all of you know that there are primarily two types of search algorithm. First one is a linear search where we believe that the array is not sorted. It's a primitive algorithm, very primitive search algorithm where we individually try and check with every item and check whether that particular item of the array is the key item or not. That is how we work. Okay, so in worst case, how many number of queries it can take? Order of n, because in worst case, it can take up to n-1 number of queries in order to tell that whether that particular element is there or not. And so that is in a big O of n. Okay, and there is another search which is also very famous searching algorithm known as a binary search. So what binary search does is it basically splits the entire given array into half each time, and based on that it searches a particular item. Okay, and for binary search there is a first one prerequisite kind of thing. What is that? That is, your array has to be sorted array. If not, then you can think of applying first certain sorting algorithm, which itself is going to take, and if you consider the asymptotic time bound and all those things, so it is going to take n log n amount of time. Okay, so in that way, how binary search works is it basically checks with the middle element. Then depending on the middle element, whatever you are getting from the array, say a middle, now it checks with the element with which it has to search. If it is less than the middle element, then again we break the array into two halves. So it's basically a divide method where we break the array into two halves. If it is less than the middle element, then we consider the 0 to mid-1 position. If it is more, then we ignore the first half from mid and we consider mid plus 1 to the high position or the end of array position. Okay, so likewise we compute, and after each time we if we do not find the element, we just do the comparison and we keep on breaking the array until we got the maybe only 2 element array which is not further breakable, or a single element array depending on that. Now we simply we do a checking, and this takes a long amount of time. But the condition that overall for an unstructured database, binary search is not applied. It is not applicable. So there we need a certain different type of search algorithm. So can we in general say that a search algorithm in classical that takes order of n amount of time? We can tell that. Okay. So this is linear search algorithm. I do not need to go through it. I hope all of you know. First, we have to check with the 5 whether 5 is the search element or not. If not, then okay, go to the next position, do a I plus 1 or I plus plus, whatever you want to do. Likewise, do another checking, and all those things we do. And this is how binary search algorithm works. Okay, you can see at if you do a in order traversal, it will always give you the sorted array. Okay, 5, 11, 12, 14, 15, or this thing basically. Okay, so 5, 11, 12, 14, 15, 18, 19. Then it is this one. Then this one again, 9, 10, 11, 12, 13, 14, 15. So you can see over here, whatever you do, it will be always a sorted array. So, okay, so It's a comparison between linear and binary search. Any random or any random order, it is a sorted order. It is preferred for small list. It is preferred for large list. Nothing like that. It is very like not really very relevant logic. List size does not matter over here. If it is not sorted, anyway, it's not applicable. So that is the thing. And it is definitely it is slow. Linear one and binary one is fast because it's long. So for a sorted array, definitely we need to go for the binary search. We do not need any quantum search there. But why we need a quantum search? Because quantum search algorithm, there exists a quantum search algorithm that can work with that precondition that it can process any random order. And it is also preferred for large lists. It is fastest among the three in terms of the random order. And array also single dimensional or whatever it is. Here the dimensionality, because anyway, whenever you are encoding certain kind of a data into quantum setup, the itself it has a different dimensions which you have to consider. Okay, superposition and all those stuff. So the last one does not hold here. And the complexity that quantum search algorithm will bring is order of root n. So again, the same thing. This is law of Grover in 1961. Is his birth year, and in 1996, and Shor's was, I guess, in 1994. Shor's algorithm, and Grover's algorithm was in 1996. Okay. So that depends on your number of qubits. That depends on how many qubits you give it. And of course, there has to be a relation. If I say, for example, you have an array of say 10,000 elements, then you have to choose accordingly how you will be choosing. What is the logic behind that? We will look into today's class. We'll understand what is the relation between the both the things. But definitely there is a way, and accordingly you have to calculate and choose or finalize the number of qubits that you need to give. Okay. Rows and columns means what you are asking exactly. See, it's just a unstructured data set I'm taking. I'm not here considering any like my multi-dimensional thing, 0, 0, 0, 1, likewise the row measure, column measure, nothing I'm considering. Okay, it's a single dimensional, just a raw data set, unstructured, unsorted data set. Can it be applied to? No, generally, okay. So generally it is applied on unstructured data, then there has to be for certain logic, you have to like mold it in this way so that you'll be able to interpret it. But why, I mean, why you need to do that? Because anyway, even whatever be the dimensionality of the array, it's ultimately a certain like linear array only can think it of in this way, in memory, right? So whatever order you are following. So just do that thing. That is a linear time you can do that. So post that, apply your browser if you want. So these are theoretical slides, just go through it. Problem statement is this thing. Say, for example, you have a certain kind of a number and n is the number of qubits. Let me just start. There is two technique. I'm ignoring this thing because I'll be explaining this one. And in few cases now there is a this error. So थोड़ा representation इधर उधर हो गया है. So anyway, I will be doing entire thing. So do not follow any mathematical expressions from these slides directly. For that, follow whatever the way we have done for Bernstein-Vazirani and all those things. We are using the whiteboard and all. Only for the text you can rely on these things, okay? Because like more of the it was PDF initially. Right now I converted to PPT, so that's why there is a bit of kind of error in that. Or later also, if you want, you can reconstruct it because we will be doing everything starting from scratch for this Grover. Okay, so this is the Grover. You will not understand anything like that. So just post these things. Few of the things we will be understanding and few of the equations are actually broken. Okay, so let me now add slides to it. So now officially we will start Grover. Okay. Let me first take a few things. I guess more number of that maybe is required. Okay. Great. Chalo, let us start. So, Grover's algorithm. Okay. So, first of all, it takes root over of n. We are going to prove why it is root over of n number of queries. And for that, let us start. Say we have, let capital N be the total number of steps. So, number of steps. Okay. So, n has to be 2 to the power of n. And number of states, say, is equivalent form of the data that I am encoding. So, data being encoded into states. Okay, and n equals to 2 to the power n, where n is your number of qubit. Okay, so here, say we have an oracle, which we call as a needle in a haystack function, say defined over this thing that 0 less than equals to k, your less than equals to 2 to the power of n minus 1. Okay, this 2 to the power n means your n is the number of qubit, 2 to the power n is capital N, or equivalently you can also write it down in this way, that k lies somewhere in between 0 to n. That is, one of the states is the one that you want to find out. Okay, through Grover. Out of the all the n possible states. It is not n, it's basically n minus 1, because 2 to the power n is capital N. Okay, and this has to happen such that your f of k is 0 for all k except for which, or except for w, where your f of w is equals to, say, 1. In easy words, say f of k is equals to 0 for all k not equals to w, and f of k or f of w, whatever you want to write, is equals to 1 for k is equals to w. What is w? W is the marked item. Marked item means the item that I want to find, or the item to be searched, say search item, whatever you call it. Okay. Now, how the Grover oracle will look like? The Grover oracle is a very basic oracle which looks something like this. Say, for example, okay, this thing, and W, why I'm writing W? Just to represent the W is a marked item. If you want to write only UF, you can also write it down. That is up to you. So your X is basically the input register. Your Y is the target register, which is also input, but input to the oracle, where you want to store your final output as, and this X will be unchanged, and this one will be Y XOR f of X. Okay, so this is the where your final target will look like. So target output, say, and this is target as input, and this is strictly the basic input state. Okay, and fwx, this fw of x is what? This is basically 0 and 1. This oracle function is 0 and 1, where x is not equals to w, and here it is 1 when x is equals to w. And if y is equals to, say, y is equals to 0 minus 1 by root over of 2. Now, whenever I say these things, say y is equals to ket0 minus ket1 by root over of 2, you have to assume that it was initially ket0. I have applied a not followed by a header mat, and I have got this thing which I have fed, and right now I want to feed to my oracle as a target. Okay, so every state you have to reconstruct. for the real implementation. But right now, let me assume that y is equals to y given as ket0 minus ket1 by root over of 2. So the output will be what? The output will be minus 1 to the power fw of x ket x product. See, here only I'm writing it in this way. Okay, the ket x I'm writing in this way, product the ket0 minus ket1 by root over of 2. Okay, and why I'm writing here in this way is because my target will now be, target can be, say, y xor fw of x. So if y is equals to 0, sorry, y is equals to 0, then it is fwx, and if y is equals to 1, it is fw bar x. So that is minus 1 to the power something, minus 1 to the power 0 for certain cases, and minus 1 to the power like 1 for certain cases. The phase inversion logic I was just telling yesterday, for only a 2 qubit 0 0 0 1 1 0 1 1, and we take 0 1 as the that one, right? So that is something we want to now build on. Okay, and if you just see, the second register is unchanged. So this is the second register which is unchanged or unaltered. But the first register, see, let me write, but the first register, this is the first register, has a phase depending on my fw of x. Okay, so if fw of x is equals to 1, then the sign of the first register is flipped, because it will be minus 1 of the first register will be flipped. Okay, okay. Now based on this, once we have designed this, now we will be defining few unitary operators. So we have to define now, we have to define unitary operator. Say first operator is UW. W is for the mark state, always remember, and U stands for unitary. W is a mark state. So which is nothing but identity minus 2 times ket W bra W. Okay, so this is the first expression. This is one operator itself. Okay, now when this UW or unitary W acts on mark state W, what will happen is UW on W. So this is an operator, that is why it is acting like this. UW, then KW. We'll make it what? This one will be I into KW, which is nothing but KW minus 2. This is KW. This is basically inner product, nothing, only this thing will happen. So this is, we all know, inner product of this thing. No matter whatever be the value of W, it is always 1, because they are same. Otherwise, it would be 0. Since they are same, so it will be 1. So it's W minus 2 KW, which is nothing but minus KW. So see, over here, physical meaning of equation, physical and geometric meaning, everything I will say. I'll just tell. See, what I want is, okay, why I am framing it in this way is because in superposed state, I have to like find out a certain kind of a generic form. Now in superposed state, I want it in this way, that if I get the mark state, that I should be having certain operator that, based on the logic, when it is applied on the mark state, it will make it like a phase inverted one, which is say minus KW, as you can see. And if it is applied on some of the any other states other than the mark state, then it should make no inversion. The operator should have nothing on it. So similarly, based on that, we have applied it. Do not write now only confuse it with the quantum circuit form of it or anything like that. We'll see everything. Just be a little patient for Grover. It's a very big algorithm. It's going to take some time. So just be patient. Now we will take a linear combination of computational basis. Okay. What I will be doing, consider this one for 0, 1. Now we have to take for the other ones as well, like 0, 0, 0, 1, 1, 0, 1, 1, except the 0, 1 thing. So we will be taking now. So we will take a linear combination of all the computational basis states. Computational basis states as our inputs. And say this uniform superposition, why uniform? Because right now I have not done any change of the amplitude. So it's all like 1 by √2 or 1 by √4 or 1 by √8 applied on all. So this uniform superposition or uniform linear superposition is say represented by the symbol S, okay, which is also known as a standard state. So for superposed form, it is nothing but this thing. 1 by √over of n, x equals to 0 to n minus 1 get x. Okay. And x is the collection of all states in the computational basis. You know now what is the meaning of x and what do I mean by 1 by √over of n. So for those who are having any doubt, this x is nothing but like this. Say example, I'm just writing, say 0, 0, 0. Okay. And likewise, it can be 0, 0, 1. For 3 qubit, I'm just writing example. And n is nothing but 2 to the power n. So root n is nothing but √over of 2 to the power n, which is 2 to the power n by 2. Now I hope you can relate with the previous like expressions while I was writing it. These are same thing. So now by definition, we can say that since Kw is one of the collection, one of the member of this, or say belongs to, say W belongs to this like set of S somewhere, or set of states, Ket S, it is one of the members that I want to find. then that implies W and S inner product will be 1 by √over of n. How I am getting it? Say let me give a small proof over here for this thing. So for proof, let me take a 2 qubit state. Say a 2 qubit. What I want to prove? I want to prove this particular thing. Okay. Proof for equation 1. Say for example, 2 qubit system I have. That means n is equals to 4. Okay. 4 number of states. So your S will be nothing but half into this thing, Ket 0, 0 plus 0, 1. √4, instead of √4, I'm writing 2 directly. Plus 1, 0 plus 1, 1. Okay. And your WS, this thing will be half into. Now, W means, what is W basically? That is something that you want to find. So let me take a W, say 1, 0. Okay. So now this means that Ket W will be nothing but if W is equals to this thing, then this one, raw W will be nothing but this thing, right? So likewise, it will be 1, 0, and this one is as it is, plus 1, 0, then this one is 0, 1, plus 1, 0, this one is again 1, 0, plus 1, 0 times 1, 1. Okay. Now, if you compute these values, what will be the value? What will be these values? Let me show these calculations. Say Ket 1, 0 is what? Yes, it will be half. So which is 1 by √over of 4 for 4 state. So ultimately, if you just compute it, for one case, I just want to show. Let me take this one as well as this one. So 1, 0 means 0, 0, 0, 1, 1, 0, 1, 1. So it's basically 1, 0, that is 0, 0, 1, 0. in this way, but it in the bra notation. So it's basically 0010 times K00, which is 1000. What is the value? 0 into 1 plus 0 into 0. So 0 into 1 plus 0 into 0 plus 1 into 0 plus 0 into 0, which is nothing but a 0. Likewise, you are understanding that this, if this is 0, this is also 0, this is also 0. Let me take this. So if it is, like, say, this particular calculation, this particular calculation will be 0010 followed by 0010. So it will be all zeros. Only for this case, it will be 1. So it will be 1. That is, this is 1. Okay. So thus, from this line, can we write directly? It is half into 1. That is half. That is 1 by root over of 4. And for general expression, if it is given for n number of state, I am writing 1 by root over of n. It will be always this value. Okay. So this is the proof for this equation number 1. Right? Now, post that, there is another operator. So first operator, what is the operator first that we have seen? We have seen UW, which is I minus 2 KW bra W. Okay, this is outer product form. Now, Grover defined another operator. Grover defined another operator, which is known as, what's it called? The reflection operator. Okay, it is called the reflection operator. And it is another operator, so it's US. And US definition is 2 times kit S, bra S. S corresponds to the standard state, W corresponds to the mark state, minus I. Though it seems like almost same, but it's like very, very different. It is not at all same with the UW. And ultimately, okay, there is another operator which will come, I will tell you. So this is operator number 2 and this one is the operator number 1. And why this is called a reflection operator? This is another question that should come to your mind. This, why basically we want this? Because this US is called a reflection operator, called a reflection operator, because operator, say why? Say we let this US, say let US work on arbitrary state, or when US, whatever you say, arbitrary state psi, then what will happen? That is what I want, US on psi. So when this type of thing will happen, any state psi or psi will be resolved into 2 components. Resolved into 2 further components. What is the first component? The component parallel, or say along, whatever you say, the standard state S, and another component which is perpendicular to the standard state S, or the like superposed state S. So that means you can write it down in this way, that psi is equals to psi parallel plus psi perpendicular. Now, whenever these kind of parallel and perpendicular things are coming into picture, you can understand that there is certain form of a geometry that is now to become coming into the picture. So just remember what we are aiming for. We are aiming for the reflection operator. It's one of the operators for Grover, but not the entire Grover operator has even come yet. Okay. Now, so what we say is if this US, okay, acts on, say, psi, then the component which is parallel to S is unchanged. But the sign of the state for component perpendicular to this thing, perpendicular to S, will change its sign. Okay. And together, these US and UW, we will see the reflection just right now. Just one thing. Together, this US and UW together, that is the third one, that which is also called the Grover operator, alternatively known as Grover rotation operator. Grover rotation operator, which is denoted by the symbol R, or also written as RG, that is nothing but your US times UW. That means this is the first operator. First you have to apply UW, followed by US. Whatever result you got, you have to apply US. That means RG on a particular state psi will be US UW psi. Okay, this thing. That means if this is psi 1 after applications, which will be US psi 1, and on application, it will, this entire thing now will become psi 2. Likewise, just in order to tell you the precedence of the operators. Okay. So these are the three operators that we have. What is operator number one? Operator number one is UW is basically I minus 2 get W bra W. Second is US is basically 2 get S bra S minus of I. And the third one is the third one is this thing, which is RG is equals to US into UW. All these things are equations for Grover. This one, 1, 2, and 3. These are Grover equations. Okay. Now let us see that how the geometric interpretation will work. Yes. So the geometric interpretation of Grover. Every single step is required because every logic here is entangled. Okay. So please focus on each and every step. Geometric interpretation of Grover. Great. So that means I had two operators now. W is my marked state. S is my superposed set of superposed states. So W marked is, say, superposed. Just writing in this way, superposed states. So it is just like, say, this, and here I have my W state. Okay. So this will be what? If this is W, then this will be W perpendicular to W, this thing. Okay. And this one is, say, for example, my S. Just like that. Okay. So this is ket S. So that means this is also ket S. And if this is ket S, then perpendicular to S will be somewhere like this. The angle will be 90 degree. Sorry for this thing. So it is S perpendicular and okay, yes, it is also S perpendicular. Okay, and say phi is that arbitrary state that right now will be operated by the all the operators of Grover. Okay, so phi is basically somewhere here. Say for example, it is this position. This is phi. Okay, say the S is making, or the superposed is making an angle of theta with respect to the perpendicular of the marked state. Okay, so if this is theta and this psi is making with respect to the W, this is making a particular angle, say phi. Okay, so definitely first one thing you should be like you must be getting, that is what is the value of this particular angle. If this is pi by 2, then this angle should be, this entire angle should be pi by 2 minus of theta. For normal logic, it will be minus pi by 2 minus theta. Okay. Now, say this particular angle that it is making. Okay. Now let us see only this thing. And okay, if this is theta, what will be this particular component? Here it is with respect to S. With respect to S, can I just write it down in this way? See, this theta is an angle that is made with S. So this one is the cos component of it and this one is a sine component of it. We can write it down. So W will also equivalently can be write down in this form. And this one can be write down in this form. Cos theta. Okay. Now say for example, I am just trying to apply this particular, first I want to apply some operator or say rotation with respect to my original state psi. First of all, what is the target? What we are here, we want to achieve through this geometric interpretation and all, we want to see that how different states and all the like reflection operator, why it is called reflection, how two operators are working, and my mark state is what? My desired state. So that is my mark state and S is my initial set of superposed state. So what is my objective? Through certain rotations, I have to reach to mark state as much as possible so that now if the arbitrary state is measured, it possesses the value of the marked state or the marked item, which in certain number of queries, we should be able to find it out. But it is definitely not that easy. It will take some time. In one iteration, we cannot get that. So initially, whenever we want to apply, okay, say phi component on application of my rotation operator will happen, sorry, my reflection operator will do what? It will break it. It will break it into two components, right? This is what we already have seen it over here, that US acts on ket psi, then the component, okay, here it is. Yes, so it actually, ket psi is broken into two components. One component is along the standard state S and one component is along the basically component perpendicular to the standard state S. Right? We have seen that one. So that means, let me change the color a little. So that means somewhere this phi will now be broken into two different components. Okay. So one will be something like this. Say for example, okay, and this will happen due to UW, so psi 1. And then another one will happen another time, again there will be a rotation due to US, and this is like, say this, just a minute. Yes. Okay. This will happen. Now say for example, this, what is the angle that it is making? Say with respect to the S perpendicular, this psi is now making an angle of chi. Okay. So if this is chi, similarly, because of the vertically opposite angles and all those things, this will also be your chi. If you're not writing, those of you will not be having the very clear understanding unless you are doing it parallelly. Okay, and this was your phi. That means if this is phi, then this one will also become your phi. That is how it is actually the vertically opposite angle and the alternate angle theorem, all those things work. Great. And if this is theta, then what about this particular thing? So this particular angle, this will also be theta, and which if you check it, it is nothing but this psi plus chi, this particular stuff. So the things are that the angles between KW and S perpendicular component is basically theta, and also that is equals to the angle between your S and W component, W perpendicular. Okay, your S and your W perpendicular. Yes, that is also theta, which is also equals to phi plus chi, and angle of rotation, this is psi 1 and this is a psi 2, angle of rotation between your initial like state, which was phi, and your or psi, and your final stage or final state, which is psi 2. So the angle of rotation between your very initial state, this thing, and the last final state, psi 2, this one will be what? Is basically, if you just take all the angles starting from this and this, okay, in between their angle, this is phi plus theta plus chi, okay. So this is phi plus theta plus chi, and phi plus chi is also theta. So theta plus phi plus directly also I could have written just in order to show you. So it's theta plus theta, which is equals to your 2 theta, right? Now just have a note on this thing. That means after applying one set of rotation operator, one set of both the operators like UW and US, okay, as we keep on applying them, so one such rotation is giving an angle deviation of 2 theta. Now, whether it's good or bad indication depends on, now the answer is it depends on whether you are converging to the marked state or your solution state fast or not. What do I mean by that is, say phi and phi 2, that angle difference after application of both the Grover operators is 2 theta. That means one iteration, in very easy language, one iteration will make an angle 2 theta. Now, if you make another iteration, it will make another 2 theta from the output state, which is right now phi 2. Now it will start with phi 2, and accordingly, again, the entire rotation will be taking place. And likewise, why are you rotating in this way? So that from your arbitrary state, where it could be somewhere like close to your superposed state, or it can be close to your marked state, your target is in the superposed fashion, you have to do it in this way so that all the other states, except the marked state, goes away. And exactly the ideal state would be towards the marked state, or should be very much closer to the marked state in the superposed form. That was your target. Okay. But there is a challenge, or there is a, not a challenge, but there is also another consideration here. That is how many iterations you have to perform. Say, for example, you are keeping on iterating, and slowly, instead of coming to a better solution after a particular iteration, maybe you are again some way you passed the mark state. So in that case, you will actually keep on rotating along the kind of these particular axes mathematically, and we will never be able to converge to the ideal one. Okay, so that means how many iterations you should be making, or how many iterations ideally one should make in order to get the mark state with the minimum number of iterations, because every iteration is terms of is called basically here every query. Okay, which is not a classical query, rather a quantum query. So you have to make as many iterations as possible so that you can get your desired state fast. So following that, now our target will be how to finalize what will be the number of iterations, because at one iteration the angle deviation is 2 theta. So that is, so let me just write it down also. Say after one such iteration, after one such entire Grover rotation, we want to exactly we want to get closer to, but what I am telling is absolutely your understanding is right. But what I'm telling is, maybe say I want to go to a particular city, but I am just running so fast, maybe that city again I'm missing. Now again after 2 theta or that much of angle shift I have done, I'm doing that much of like rotation. After 2 theta, again I am watching what is my deviation. So again, I can see a big deviation because maybe just now, just during that like rotation, I crossed it. So that is not doable. So there has to be a like strategic way to pause, or kind of a what to say terminating condition in recursion, kind of that. You can think it of in this way. There has to be some base condition after which you should not be performing any iterations. Now the thing is, now we will check that on what factors these things are dependent on. How they are dependent. Okay, so after one such entire Grover thing, entire Grover reflection operator, okay, the angle between initial quantum state and final quantum state, initial and final quantum states are 2 theta, 2 times theta. Okay, so question is, initial superposed set of states will contain say 100 states, out of which 99 are not desirable and 1 is the ideal state. Our target is through this rotation operator that how our objective will be that how easily and how fast we can converge from S, that is the set of superposed state, to W. That is my question. Okay, so my question is how to converge from S to W. It is a set of superposed state, it is a marked state, or the desired state I want to. Say from 100 states I have 99 desirable. So I have to, 99 not desirable, and 1 is the ideal state. Okay. So your entire 100 state whole superposition slowly needs to come to that one state, boils down to one state. Okay. Now say first arbitrary state, which was say psi, that was divided into 2 components. Sorry, first, okay, no issue. So this thing, parallel and perpendicular, and the angle between S and W perpendicular, this was theta, and angle between your S and W, what it was? Say S and W, I want to see. So S and W, it is pi by 2 minus theta. Just check S and W, this pi by 2 minus theta. Okay. Now say we have a 4 input data. Okay. That is, I have 4 number of inputs that I want to do. Great. 4 input data means number of input here is equivalent to number of states. No, it is equivalent to number of states. So if I have 4 input, I should be taking 2 qubits. but my number of states should be equals to 4. So 4 data means 4 states. Okay. So the initial angle between S and W is what? Is basically, I can write it as cos phi theta dash, where theta dash is basically nothing but the pi by 2 minus theta. I can write it down in this way, considering pi by 2 minus theta, just the sine component, cos component wise, just take it. And S and W, that angle I'm taking as a pi by 2 minus theta. So it will be sine pi by 2 minus theta, which is basically your cos theta. Not theta, sorry, sine cos pi by 2 minus theta, which I am taking the cos component. So instead of writing pi by 2 minus theta, I'm just making it a cos theta bar. Okay. This is the cos component, nothing else. This is what I'm telling. With respect to this theta, it will be, I can write it down with respect to the pi by 2 minus theta. That is why I'm writing cos theta bar. Okay. If this is S cos theta, it will be cos theta bar. That is it, nothing else. Okay. So now from a cos theta bar, I got it over here. So I can write it in this way, that it is nothing but, if I want to calculate it, then it is S W by S bar amplitude and W bar amplitude. I can write it down. Okay, so it will be nothing but, to just take the value for n input state, it will be half post, this one will be root over of this half square and all those things. So this is 1 by root 2 whole square times 4. If you calculate it, you will be getting the value half. Okay, so your theta bar will be cos inverse of half, which is 60 degree. Right? Therefore, your theta bar is equals to pi by 2 minus of theta. Therefore, what is your theta? Your theta will be definitely 90 minus 60, that is 30 degree. So your theta is 30 degree. Does it mean that your rotation angle is by 30 degree? No, because your rotation means every grover will make it 2 theta. So that means that a single grover will rotate from the initial state by how much? Rotate by 2 theta, that is 2 into 30 degree or 60 degree. That is the ideal rotation that you have made. In order to do what? To align your S with to mark stack W. Okay. Now say n is equals to 8, another one. So similarly, if you compute, you will see that cos theta bar is 1 by root over of 8, and theta bar will come somewhere around 69.29 degree or say 70 degree, whatever you say. Okay. So in that case, theta will be how much? Theta will be around 20 degree. That means now a single rotation will make how many such rotation? 2 into 20 degree is equals to 40 degree. Likewise, it will keep on rotating. So often by keeping on rotating, we might exceed the mark state. This is what I'm telling. So my rotation is not really very much fixed. So the thing is, by keeping on rotating, the problem is we might exceed the mark state. We might exceed the mark state. Okay. So this will do what? And if this happens, so your unnecessary rotations will take place. Unnecessary rotations. And definitely each rotation means a lot of one query almost. So if your query increases, your complexity, cost, everything will increase, and we will be seeing less amount of quantum advantage. So for that, the question was how many suitable rotations, how many number of rotations are really suitable. Okay. So now we want, so our question is now that how many rotations are suitable. Okay. So let us look at. Say if I have, where is it? Yes. Say if I have psi is equals to AX is the probabilistic amplitude, X. This is all we know. So S is nothing but 1 by root over of n, X equals to 0 to n minus 1, X. Then your S and phi will be 1 by root n. Okay, the inner product of S and phi, it will be 1 by root n times this thing. What? Say I am taking X and X bar. Both the things are same because here in both cases I have X and X. So I'm just taking one to be X and one to be X bar. And this AX times this X followed by X bar. I hope this is very clear because both the cases are like X. That is why I have taken one to be X itself and another to be X bar. And since this is ket bra S times ket psi. So likewise, I have to write over here this thing. And AX is as it is. Okay. Now from this thing, can we just write it in this way that 1 by root over of n times this AX only, where X is equals to 0 to n minus 1. We can write it down. Why? Because if X is equals to X bar, then X bar is basically is equals to 1, else it is 0. We have seen already these things. X bar, so that will be 0 if X is not equal to X bar. Where we have seen it? So 0 and orthogonality and all those things, we have checked it, right? So 0, 0 will be 1 or 1, 1 will be 1, but 0 and 1 inner product, if it is 0, so like in inner product, it will always be 0 if it is not same. So likewise, from this equation, inner product of S and psi, we can write it down this equation, this expression. Okay. Now from this, let us do one thing. What we will be doing? We will be now calculating mean amplitude. Mean means what? The normal average. Okay. What we want to calculate? We want to now compute the mean amplitude. So mean amplitude, let me write it in this way, A bar. So A bar is nothing but sigma AX by N. This is known to all of you, like A1 plus A2 plus A3 plus A4 by number of states, which is 4. Sorry, this thing. Yes. Is my voice breaking or is it okay?
It's okay, ma'am. I think.
Okay. Okay.
Yeah.
Okay.
Yeah, please check at your end. I think the voice is very clear for us. Thank you.
Thank you, sir. So now where we were in this position. So we had something. Let me just write it down. Okay. This last expression once again. So we had something like this. So Kate, this kind of thing in a product of SW, which was 1 by root over of n times sigma x AX. Now we have this thing. Now here, in place of this sigma x, if I write it in this way, that n into a bar, definitely we can write it down. So it's 1 by root over of n times this this thing, that is n into a bar. Okay, simple from the multiplication, cross multiplication way I'm writing it. So okay, 1 will be cancelled out, so it will be root over of n times a bar. Okay. So it is always be root over of n times a bar. Now what is a bar? A bar is a constant. Is a bar anywhere related to any of the values instead of a constant? No, it is just a constant. So from this, we can have an idea that ultimately these three, the relationship between the s and psi, that is a factor of root over of n. Okay, and this is a constant. See, now once I have a particular n, it is a constant. It's only a dependent on the number of states, not on anything else, not on the s state or the w state anymore. So that means that it determines that I can, in worst case, require for the like rotation operator maximum root over of n number of rotations, not more than that. So it is a function of root over of n. Okay, now us, that is the reflection operator. Once that is applied on ket psi, what was the expression? It was 2 times ket s minus I. It was the operator itself. This is us times ket psi. So it is nothing but 2 ket s. Then this thing, I can write it down like this, minus ket psi. So in place of this entire thing, let me just write it root n times a bar. So if I write it, it is basically 2 into ket s times root n into a bar minus ket psi. So from this, I can write it down. Now, root s is nothing but, I know, the superposition of that particular thing, x, right? Ket s is nothing but that one. So I can write a bit of like, idhar udhar karke, we can write it down in this way, that 2 into root n into a bar into this root s. Can I write it down in this form? That's 1 by root over of n times sigma x ket x. That was the very basic our like assumption, that S is a set of superposed states of basis states, and x ket or ket x represents all the basis states. Okay, so we can definitely replace S with this thing, and times this is ket psi. Let me take like write it. Where is it? Okay, so this is nothing but ket psi now. So this root n will be cancelled out. So this will be 2a bar sigma x x. Now instead of this psi, can I write it down in this form, that it is sigma x ax and x? I can also write down in this way. So this is ultimately, just take a sigma x as common. So it will be 2a bar minus ax, this amplitude, times ket x. Okay, so this is an alternative representation of this thing. Us ket w is nothing but this thing. Now our objective is to find the interpretation. Next objective is to find the interpretation of application of this thing, application of US on psi. So US on psi is basically sigma x. Now I have this 2a bar minus ax times ket x. So before your US is applied, amplitude, what was your amplitude? Amplitude of x in ket psi, this was ax. Okay, and after your US is applied, amplitude of x in psi is 2a bar minus ax. So the amplitude, this thing, AX, with respect to mean is nothing but A bar will be what? It will be AX minus A bar. Right? So it will be AX minus A bar. Now, amplitude with respect to mean, for the final one, if you again calculate, this is with respect to say 3, this is 1, this is 2, 3 is with respect to 1. If you do that, it will be, initially it was what? 2A bar. So it's 2A bar minus AX. Now it will be minus A bar with respect to this. So it will be A bar minus AX. So it is nothing but minus of AX minus A bar. So in that way, say this is 4 and this is with respect to 4, with respect to 2. Now if you see, this is an inversion about a mean. There is a form of an inversion at least. And with respect to mean, it is happening. So that means we can clearly see, let me write it down, inversion. No, right. Okay. Yes. So you can see a inversion about mean. Why inversion? Because of this thing. And why with respect to mean I'm calculating? That is why it's called inversion about mean, or inversion with respect to mean. Okay. Now, say for example, now we have seen two things. First was the phase inversion one, and we also have seen that inversion just have introduced a new process, and just for introducing this thing, we are doing all these kind of like relations. So just a quick recap of what and how much effort we have put just in order to get this feeling of inversion about mean is basically we started with the geometric interpretation, even before that also the reflection operator. So we are keeping on doing it because once the phase shift or phase change operation is done, that particular stuff is over with respect to your UW. Post that, you have to do your inversion about mean. And for that calculation, there are so many factors that have come into picture. Okay. After all these things, right now we are in a position to see practically with respect to a particular input item value that whether literally this kind of an inversion makes any or how it amplifies the particular say probability or amplitude, whatever it is. So which was the very essence of quantum amplitude amplification. So yesterday I was talking about it, that QAA follows the logic of that particular thing. What is it? Like QAA or quantum amplitude amplification is one of those techniques which are followed in Grover. So here actually you can see the real effect through the inversion about the mean and all these methods. For that, let me take an example. Let me take an example. What is the example? Say I have total n number of states. Okay. That is, I have a total number of states is n equals to 8. 8 number of states. And my oracle, after application of FWH already has FWH, okay? So it already has the knowledge of the mark state. Okay, that is, the marking is done. We are assuming this thing. Okay, so say W is equals to 4. That is, for a n equals to 8 number of step means n equals to 3 number of qubits, and W is equals to 4 means I have to write it in this form, which say 100. So W or the marked item is 100. Another one thing, so how your S should look like, it will look like this, 1 by root over of 8, get 0, 0, 0, plus 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, then 1, 1, 0, plus 1, 1, 1. Okay, so just notice that in S, every amplitude is 1 by root over of 8. That is amplitude of each of these states. Each of these states is basically 1 by root over of 8. But after UW, it is a bit different. It is now 1 by root over of 8 times 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1 minus 1, 0, 0 plus 1, 0, 1 plus 1, 1, 0 plus 1, 1, 1. Only this particular thing had happened. Okay, so amplitude of all after UW is 1 by root over of 8 except for the marked states amplitude, which is minus 1 by root over of 8. Okay, so after UW, amplitude of W is minus 1 by root 8 and amplitude of anything which is not W is equals to plus 1 by root over of 8. Okay, so let me calculate the mean amplitude. What will be the mean amplitude? So mean amplitude will be a bar, whatever you call it like. So it's basically 1 by root 8, all the 7 times it will happen, and only for one value it will be minus 1 into 1 by root over of 8, and whole this thing whole divided by 8, a1 plus a2 plus a3 minus a4 plus a5 plus a6 plus a7 divided by total 8. That is what I am doing. Okay. So it is basically 1 by 8, just a calculation. If you do it, you will be getting like this thing, 7 by root 8 minus 1 by root 8. So yes, so 6 by root over of 8 and all those things. So it will be 3 by 8 and root 2. This is the mean amplitude on A bar. Okay. Now we want to apply what? We want to apply the US. Now it's time to apply US. So new amplitude of all these states we have to calculate. Therefore, the new amplitude of all states will be what? 2a bar minus ax. It is basically the, what it is? 1 by 4 root 2. And what will be like all states except W. And amplitude of W will be 2a bar, which is 2 into 3 by 8 root 2. Let me just write one line here. 2 into 3 by 8 root 2 minus 1 by this thing, root over of 8. Because it is 8 is plus 1 by root 8. Here we have a minus, so this is the thing. But here it will be 2a bar minus ax, where it is minus of 1 by root over of 8. Why I am writing it? Because just to show you that how, because of the inversion and the US operator, because the phase was inverted, now I am applying US operator, how beautifully it is amplifying it. So it will now become, all these things, it will be added up. If you calculate it, you will be getting somewhere around 5 by 4 root 2. Now just see, we have something like this. So all the other values were initially were in this position, 0, 0, 0, 0, 0, 1, 0, 1, 0, then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now once we are applying UW, what I am doing is, it looks something like, say, W is equal to 100. Only this one was inverted. So 000 is up, this is up, this is up, and this one is also up. Now this is down. Now this is up, up, and up. Now post that, whenever I am applying US operator, okay, what I am getting? Ultimately, I am getting all these values to be very small. And this, because of the negative and negative, both my negative effect, it has now become very positive. And this kind of that. So the maximum probability will lie to the one where you have your marked state. All the remaining state probability will be diminished. And because of the normalization and all those things, ultimately it is also still like, even after all these things, it is normalized, as well as the other probabilities are like adjusted in order to make this probability amplified. This is the probability, means amplitude, and like amplitude square is basically probability. So this is a quantum amplitude amplification. And how much of amplification you are getting over here? Initially it was 1 by 4 root 2. So almost 5 times amplitude amplification you are getting. So therefore, your amplitude of marked one, which is your desired one, amplitude of marked state. The thing is, if I directly just tell you, just apply US, which is 2a bar minus ax, it does not make any sense. That how, what is a, what is ax, and what is uw, what is the relation. And only for this particular expression, we have to like travel through the entire ocean of different interpretations. So amplitude of marked state will be 5 times here the amplitude of the unmarked one. Unmarked means, yes, which is not, say, the item to be searched. Okay. So also because this is the like 5 times our amplitude is getting amplified. So this is known as, this is known as what? This is also known as quantum. What is the problem with this color? This is, just wait a minute, it will come. Yes. Okay. Yes. So this is known as quantum amplitude amplification, or QAA. Okay. So this is your QAA. And now if you notice also, there is another point to note, that is the corresponding probability density. Just check it. The corresponding probability density for marked state has become 25 times. Why? Because 5 is the amplitude. So probability means it's like a square of 5. So 5 square. That is 25 times than that of unmarked state. Okay. Now the thing is, let me look at the time. What is the time now? Just a minute. I will be keeping all the
5:10, ma'am. 50
okay.
minutes more.
Okay. Yes. Okay. So yes, all of there. So now the thing is, I was discussing that one Grover rotation. I'm coming. One, it's not ended yet. One Grover rotation is 2 theta. How many rotations I need? That kind of a direct calculation I will be now doing. Okay. So I need Say, for example, say I need m iterations. I need m total iterations to bridge the gap between my S and W. Okay. And what was the angle between S and W? If you have, do you remember what was the angle between S and W? It was pi by 2 minus theta. Just check. This is your S, this is your W, this is the angle which is pi by 2 minus theta. So which is pi by 2 minus theta. That means I have to make this much of rotation. That is, my right hand side has to be pi by 2 minus theta. And one rotation makes a something with of 2 theta. How many iterations I can maximum allow? Say, for example, I want to calculate, which is m. Now, if you solve for m, you will be getting a value like this. Say pi, just do it. So you'll be getting pi by 4 theta minus half. Okay. So now if I just write it in this way, say pi by 4 times 1 by theta minus half. Okay. Now sine theta will give me 1 by root over of n. It was initially like 1 by root over of n. Where now say, for example, what is the value? Directly from this, can I just write that theta is also equals to 1 by root over of n? Let me tell you why. Because first of all, when theta is very small, what is the value of, what is the series expansion of sine theta? It is basically theta minus theta cubed by 3 factorial plus 3 to the power 5 by 5 factorial and so on. Right? So, ignoring the higher order terms, if theta is very small, sine theta behaves like a theta. So in that way, I can tell directly that theta is equals to 1 by root n, which if you apply over here, so it will now become, that means 1 by theta is equals to root over of n. So your m equals to pi by 4 into 1 by theta minus half now becomes pi by 4 times root n minus half, which says m, number of iterations, is a factor of VGO of root n, which also claims, says that maximum all these kind of root over of n iterations are required in order to search or apply Grover, search an item. So equivalently, that means if root over of n number of maximum number of iterations are allowed, that means, and also if you want to check, you can check it. So just take anything. Say, for example, take a data of say 1000 data elements. Okay. So just to plot it, how many qubits you will be requiring, considering it will be within that range. Okay, the data that we will be taking. Now, since here also focus that the range means the number of qubits that you are taking. So every number you will be putting with respect to a certain kind of an index. So you will not be directly returning the number, rather you will be returning the index where your number is present. Okay, so keeping all those things in mind, so just try to plot it and try to have a certain kind of an like data, and based on the data you have to make a log of that data, field value of it, right? Those many qubits you will be requiring. Now based on those many qubits and those many states, just try to plot the values and check. Then in worst case, if you increase, what the point here is, if you increase the number of iterations to be somewhere more than root n, one more iteration or say two more iteration, it might not be really that much of useful in terms of the values that you will be getting. So if you plot the values in graph, you will be not seeing a really kind of a good advantage. So this is the optimal one, and this is the maximum number of iteration that is possible. right? And why you will be seeing a bad result after that? Because of the rotation stuff. Okay, that is the thing. So for 1000, it has to be like root over of that. For 4096 data, just try to take something which is in power of 2, then you will be able to do that checking easily. Okay, now just that so originally the angle between that thing, the angle between, okay, I should be writing black. So remembering the original angle between S and W, that was pi by 2 minus theta, and after one iteration it get increased by 2 theta, and after m iteration, what will be the state of it, say for example. So after m iterations, m number of iterations, the angle between your S and W will be something like pi by 2 minus, this will become your 2m theta plus theta. Okay, so it will be pi by 2 minus of 2m plus 1 times some theta, and amplitude of W in at S. In order to calculate that, say I want to find sine of 2m plus 1 theta. All these things are coming from the like sine component and cos component from that particular geometric representation. Just by putting the values over here, say I'm putting the values of m, what I got in earlier case. So it's 2 into pi by 4 into root over of n. I got this value just before that, this page done that, plus 1 times theta. So this is nothing but sine pi by 2 plus 1 by root n. So you can write it down as sine pi minus pi by 2 plus 1 by root n. Why I can write it down? Because sine of 180 minus theta is basically sine theta. Okay, so we can write it down. So that means it is also possible to write in pi by 2 minus of this 1 by root n form. You can write it down in this way just by like multiplying minus with respect to both the values, and sine pi by 2 minus anything is basically cos. So sine pi by 2 minus 1 by root n, once I have it, I can write it down as cos of 1 by root n. And cos 1 by root n on expansion, it is nothing but, we know that since, say for example, cos theta is nothing but 1 minus 1 by this thing, 1 by what I was telling. Yeah, so it, yeah, directly by writing it, so it's basically 1 by x square by 2 factorial, yes, plus x to the power 4 by 4 factorial. Likewise it goes. So here just replace x, replace your root for x, okay, cos x. So in place of x, just replace by 1 by root over of n. Let me remove it. Yes, so it was for cos x. So in place now of x, just replace by 1 by root over of n. So it will be 1 minus 1 by 2 factorial times 1 by root n square plus 1 by 4 factorial times 1 by root n to the power 4 likewise. Okay, so again ignoring the higher order terms here. So from this, what I will be getting, say cos 1 by root n is 1 minus half 2 factorial into 1 by n, which is 1 minus 1 by 2n. So where I started with, that is sine 2m plus 1 theta, that is basically 1 minus 1 by 2n. Okay, now post the root n stuff, why I'm doing this? Because of another matrix form of representation. Okay, just to show you matrix form of Grover representation. So this is to show you matrix form, geometric form, algebraic form, all are over. So it's matrix form of Grover. It is nothing but, say I have a matrix. So here we introduce a concept of a diffusion matrix. So diffusion matrix Dij will be equals to minus 1. I'm not going to derive it. Just remember it as of now as a formula kind of. If, because it's again a very big story, not required. For a diagonal entries, and this is 2 by n for if I is not equals to j. This is a diffusion matrix. N is the number of states. Let me write, n is the number of states. I and j corresponds to the respective positions in the matrix, and 1 and 2 are, these are nothing but the numeric values. Okay. And then from this, you can also write it down in this way, that capital D is equals to, this is how the entries will be mapped. This is not the matrix, rather diffusion matrix entries I should be writing, because Dij is how you will be calculating in this way. Okay, and your matrix itself is D equals to minus I plus 2 times J by N. What is J and what is I, or everything? I is your identity one. What will be the order of the identity matrix? That depends on what is the order of your state vector and all the J vector. Based on that, you will be have to adding it. J is a n cross n matrix, where each entry is 1. Each entry is 1. Okay. And this J by n is a projection operator. Projection operator. Meaning J by n square is equals to J by n. The definition of a projection operator. So this is the matrix, and this is how entries will be filled up. Okay. This is how you can do that. For example, just for example, some entries, how it might look like. Okay, let me just do it, then we will see some example. That means this D, this is a matrix ultimately. So if it is applied on, say, initially it was A1, A2, A3, dot, 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 till say AN, where I have total n number of states. Okay, so this is this thing minus I plus this 2j by n times this thing. These are all the amplitudes of the n states. Okay, so A1, A2, likewise till it is AN. Great. So if you calculate it, you see the values from this, what it will come is basically 2a bar minus a bar 1, 2a bar minus a2, likewise 2a bar minus a n. This is how you should be getting at the output. Okay. For that, say for example, okay, let us just show it once. So let me take for say n equals to 4. 4 number of states. Okay, so your J will be nothing but what? J will be a 4 cross 4 matrix with all entries 1. That was the logic, right? So it's a all 1. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. What will be your I? It's a simple identity matrix. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And N is your 4. Definitely. Okay? So I will be taking A1, A2, A3, A4. So amplitudes are, instead of any real value, let me take in this way, A1, A2, A3, and A4. So our task is to go from LHS. Let's see what will happen. So it's minus this thing, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, sorry, 0, 0, 1, 0, this is 1, 0, and 0, 0, 0, 1. Plus 2 by 4, so it's half basically. Let me write 2 by 4 times j, which is this thing 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1. And this entire thing, let me first calculate. So part of LHS it is. Then we will apply it on this entire matrix. So what will be the value? Final matrix is how it will look like. So this is minus 1. Okay, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. This thing plus, let me write it now. So it's half multiplied by all. So it's all half, I guess. Right? It will be half only. So half. Okay. Now we will be simply doing the addition. Do the addition and do the checking. Just add it. What will happen? So from this, let me write it over here. So it will be minus 1 plus half, which is minus half. So it's minus half, then all values are half. Similarly, here it is basically half and only minus half for this one. So sorry, yes, I want to keep. Okay. We were here. Let me just add few slides, just a minute. Yes. So it will be something like that. Okay. I have to make it a full screen. So now it's half, minus half, half, half. Similarly, half, minus half, half. And the last cell, you all are understanding it. It's basically half, half, and minus half. It's the last cell. Okay. Now, this entire matrix will be applied on A1, A2, A3 till AN. Okay. So, minus half, half, then it's like half, minus half, and half, and it's half, minus half. This entire thing will be operated on A1, A2, A3, and A4. Okay, so it's minus A1 by 2 plus, so of course a 4 cross 4 and it's a 4 cross 1 matrix, so result will be a 4 cross 1 matrix. So it will be minus A1 by 2 plus A2 by 2 plus A3 by 2 plus A4 by 2. Likewise, it will be A1 by 2 minus A2 by 2 plus A3 by 2 plus A4 by 2. Similarly also here also, because all the values are same, because in RHS all the values are same almost, the structure is same. Let me just take till this one. Okay, what was the right hand side expression? It was a 2a bar minus a1, 2a bar minus a1. Okay, so what is a bar? What is a bar? A bar is nothing but a1 plus a2 plus a3 plus a4 by 4. So 2a bar will be nothing but a1 plus a2 plus a3 plus a4 divided by 2, right? Which is a1 by 2 plus and all these things. So it's basically a1 by 2 plus a2 by 2 plus a3 by 2 plus a4 by 2 and minus a1, which is minus a1, which is a single value. So just by minus a1, it will be only this thing, minus a1 by 2. All the values are exactly true, and it is basically, sorry, it's 2, a4 by 2. So it is the same entry as you can see here. Now see, this is an entirely different form. It was in a matrix form. We started with the geometric form. Both are completely different, but still the 2a bar minus a1, the inversion about the mean concept, even here also is same. And imagine this much of work Grover has done. And right now we are so blessed to have just a function called Grover, which can take any input and give you the output. But these were all the work that, and all these things he discovered. And the primary essence of quantum amplitude amplification also. This is the beauty of. Okay. Yes. So almost we are about to end. I also cannot stretch it for more time now. And we are anyway about to close. So just a few more things, and last we will end with the final quantum circuit for Grover. Okay. So I guess the proof is done. So D, the diffusion operator, this on this thing will give whatever I have here, 2a bar minus ax, which was the final expression, times kx. Okay, and D is also equivalent to WRW. Remember this thing, where R is the selective phase rotation. R is called selective phase rotation, and this W is basically the Walsh-Hadamard transform. Okay. So after this, let me draw the circuit in a fresh page. So it's kind of this, the Grover quantum circuit. It works in this way. Again, it is not like wait for some minute. Okay. Okay, few pages have disappeared. Why? Oh my god. Oh, no issue. Oh, no. Sorry. Yeah. So, so this is the one. Previous slide is there. Yes. So this is the one 0, 0. Likewise, it will be till 0. And it will be a Hadamard get. This thing. This is a Y, which is, or say, let me also, I can write, okay, ignore it. You understand it. It's a 0. And this thing I'm feeding by √2. All these things, the output of Hadamard and everything, now I'm feeding to a Grover oracle. So it's a UF, it's a Grover oracle. Okay. Then from this thing, yes, from this thing, it goes to a diffusion one, which is nothing but the WRW thing. Okay. And whatever you are getting as output, so this, now again, that will be, and also from this thing, just like the oracle works. Let me write it this way. So now again, it will go to another, this entire thing, UF, this UF, followed by this thing. This is for all the qubits. I'm putting the dots here. Then D. Then again, this output will go. This is likewise. If I go like this, okay. How many times I have to do? I have to make this entire thing. How many times? Root over of n times. So this is this entire thing now. Again, I'm repeating here. Again, I'm repeating. Likewise, I have to keep on repeating. Maximum how many times? Maximum, I can repeat it for root over of n number of times. And this is called the rotation operator or Grover operator for first iteration. This is Grover rotation operator for second iteration, likewise. Okay. So in general way, if I want to write rotation operator, this is Grover rotation operator, which is a combination of both UW and US applied in the respective order. Rotation operator. Okay. So it can have a value RG, say T, such that T is T equals to, it can start from 1 to maximum of √n. And finally, at the end, you have to do your measurement. Okay. You have to do your measurement. So this is the end of Grover. So this is finally, we can say, officially we can conclude for Grover end. Right. So how much time is left? This Grover journey was good for all of you. 20 minutes. Okay. So for 10 minutes, what I can do is I can just discuss some of the sample questions for tomorrow or for anything actually, something we can do. This is how we can utilize, because it is few things we can do. First of all, Shor's algorithm is not doable. I've told you. Quantum cryptography, formally, Grover algorithm application is amplitude amplification. Okay, let me tell you another application. Say Grover algorithm is directly for the database search, but the fine essence of Grover is the amplitude amplification technique, or the QAA. That has a huge applications. For example, there was a paper like with me and others as well, for a ant colony optimization. There we actually tried to have a novel quantum and colony optimization algorithm, but it was not for the NISQ era, for the noisy era. It was rather for the fault tolerant era, when these kind of fully we had assumed that when a fully commercial quantum computer will be available. So that is, what does it mean is, we have not thought of the idea of restricting the number of qubits or any hybrid subroutine. So it's a purely novel quantum algorithm. So there, for the pheromone, those of you, if you have certain knowledge of the ant colony optimization, there is a concept of pheromone. I will be doing the quiz practice, just 1 minute. So there is a concept of pheromone, which we believe that ants, in order to mark their trail, they keep on like putting the pheromone. And how we identify that which is the maximum like pheromone, or where exactly we can have the maximum pheromone deposition, that depends on the path that the maximum ants have chosen. So generally we thought of the whatever is the minimum, because in every path some pheromone will be put, right? So whatever is the minimum path, there it will take more time to evaporate, because more number of pheromones are eventually to be put on that path. Say I have to traverse only 10 steps. I'm also doing it to and fro, and I have to cover 100 steps. And every time I'm throwing certain kind of chemical or certain kind of anything, say. So of course, wherever I'm putting like 10 steps only, or the path is very short, I'll be putting maximum number of pheromones. So keeping that logic, now maximum number of pheromone deposition and all those things, for that, what we did is, basically we encoded the all possible paths that ants might choose. And we tried to encode entirely all those paths into qubits as qubit states. Okay, entirely we encoded the paths. There was a choice that we could have encoded the nodes or the edges of the graph, but we encoded the paths, and depending on the path encoding and the weight on that path, okay, weight on that path, we devised, or we particularly like kind of done certain tuning, or that kind of tweaking on our amplitude amplification technique, where the amplitude of the shortest path will eventually get amplified with courses of time. And it also was happening dynamically. That is, at every time, whenever that path or someone will step into that path, what will happen is that particular path's amplitude will get a certain kind of, it will increment by a little amount. So see, this is almost like a iteration number 1, iteration number 2, iteration number 3, kind of a similar idea. So we ourselves use that idea, and in multiple applications, you can see wherever your ultimate target is to find a particular item, or in order to, how out of all possibilities, how you can amplify a particular possibility. Okay. There only you will be needing the Grover, because there is no other technique that defines QA other than Grover. Okay, so this is the thing. Okay, great. So few questions. Say for theoretical questions, so what you should be like going through in a detailed way is the quantum mechanics. Let me write it down itself in the slide. So for theory, what you should be doing is definitely some irrelevant questions will never come. Don't worry about it. That is, who, when, on which year this thing was discovered. It has no use to ask those questions. So go through the superposition, entanglement, and all those stuff. How many questions, sir, you have told that it will be, I guess, 15 or 20 questions. Based on that only, I'll be like doing it. So no cloning. Thank you so much. 20 questions. Thank you so much. So superposition, entanglement, no cloning, measurement, all these things. So now, of course, at least very easily you can understand that from no cloning, chances of mathematics is less, and from superposition, maybe some questions will be asked. So few things should be very clear to you, like what is the difference between probabilistic amplitude versus probability, conceptually, and few properties of, for theory I'm telling, for few properties of Hermitian, skew Hermitian unitary, just go through that one. The inner product concept should be very clear. The inner product space, Hilbert space concept should be very much clear to you. Concept of, then comes for theory. For theory, yes, definitely the difference between classical and quantum states. Since I discussed a bit about the complexity classes, just focus on that one. A bit, only that much is required. I also do not know what more theory, or is there anything that I'm skipping? Some of the logical questions, I can just tell you some questions. Say, for example, not purely theory, but not directly very numerical. Say, I can give you questions like, in order to encode this particular, say, this much of, definitely. आज इसीलिए इतना मतलब, we all are giving effort. You are listening, I am just doing it. And just before the class also, I was again doing the same thing. So then, because these things are very complicated, so of course questions will come. But definitely, because it is mostly like MCQ or multiple select type, so you will not be asked to define anything or just draw any quantum circuit and all. So basically, fundamentally, the type of 8 questions that I had shown to you, all the questions to what will happen or how to interpret a quantum circuit. So that kind of questions you can definitely expect. So maybe for example, I can give you something like this with a certain combination of gates, any random thing. Let me tell you. Okay. So how to give you questions like, say, I will keep a certain dotted line, right? Then at this instance, what will be the value? Likewise, I can give you multiple outputs. You have to tell what is the output, or say certain kind of a quantum algorithm, or certain any random algorithm, because algorithms are very fixed. So you will obviously be knowing what is the output if we measure it. So that is what we can do is, maybe at this instance, if I apply a measure get on this, what will be the output? Okay, or maybe a part of the quantum circuit ऐसा भी हो सकता है कि, for example, say phi is equals to, initially it was 30%, 70%, we make a certain change in the probability. तो वैसा question आ सकता है. Say for example, a gate is little, it has a C0 gate with a certain kind of probability. So probability related and basic algebra, so you have to just put these things into it and इससे questions आ सकते हैं. Please go through Bell state and the basic construction of Bell state as well. Okay, because since it is MCQ, it's not a like written type, so we can do one thing. I might do one thing. Say I'll be writing it PQ, and I'll be writing it in PQ, where maybe I will be telling what is the value of P and Q. That question can be asked. Say PQ, and I'll be giving you plus. In that way, I can give you any random circuit. Then I can give you like PQ plus, say QP, likewise plus minus. Likewise, I can give you questions. Not necessarily we need to have like all the 4 options, but it can be like PQ, PP, and then QQ. तो ऐसा करके कुछ. There can be a big state. I might ask you that what is the probabilistic amplitude of that one. Definitely, if it is very much of a that thing, that uniform probability, then you will be able to understand it, or can tell me easily, very easily. So might be there, it might be the case that you will be given something else which you have to find out. Say I can also give, say, I don't know whether these values will work or not. For example, I'm just taking, okay, say get 0, 0, 0, plus, okay, let me do it for 4 now. These are arbitrary values. It will not be normal. I have not calculated it, but I'm just telling you, say 0.101 times 0.1 plus, say, gamma times, say 10 plus, say, point something, whatever it is, say point some, okay, just a minute, say 0.25 times something, as a, anything like that. Now I will ask you that what is the probability of finding the state 10? So simply calculate gamma and then it will be like gamma square. Quiz I don't know. That I have not done. You should only focus on concept. Nothing else you should focus on. So whatever content you have, if you just put, if you have understood in class, if you just go through for 10 minutes per day, only to go through the entire thing. And if you have understood it, it is done. So do not focus on any particular part, theory or it is just purely conceptual. So what you should be focusing on? Nothing. Very basic, some question I can give you that in quantum, say Bernstein-Vazirani, in classical, how many total number of queries you have to make. So I might give you questions like 2n, I can give you like n plus 1, I can give you n by 2 plus 1, and then I can give you, say, n plus something like that, say n minus 1 kind of. So you should be able to tell that it's n by 2 plus 1, likewise on you. Last, voila. 1 minute. Just give me a minute because I also have to check. 8th one. Was it the last circuit that was given in that image that I gave to all of you to solve? That 8th question, right? I guess so. Okay, there is something else. There was something. There was some circuit. I don't recall it now. It was because of interruption. I know. What are all the gates? Just tell me what were the gates there? Hadamard and Hadamard, C naught, Toffoli, phase, C phase, all these things should be there, na? Anyway, you should be able to do that. No issue. No issue. Control phase. Okay, okay. Let me take just one thing. Say this thing. Z control P. What is P? Control Z, I guess you are asking. Oh, simple phase gate tha. Acha. It should be Z, not P. It should be only Z. Okay, it should be only Z. Yes. I guess this will be like over. This will be helpful. So initially we had 0, 0. And here I will be having ket 0 plus ket 1 by root over of 2. And here it is only 0. So whenever this kind of situation come, let me write it down. So T1 is nothing but ket 0 plus ket 1 by root 2 product ket 0, which is nothing but swap. Guess what? Also there. Acha. Swap. So it was 1 by root 2. Then it's 0, 0 plus 1, 0. Okay. Now a C naught. This is the control. This is the target. By similarly here as well. So it's 0, 0 plus 1, 1. 0, no change. 1, change. Done. Now a phase gate. Phase gate is applied on which one? That is the first qubit. First qubit में phase gate है. ठीक है? Phase gate means what? You have to apply 1, 0, 0 minus 1 thing. Okay. So first one, so here it will be 0, 0 only, nothing will happen. And this one will now become a minus 1. This is not a controlled one or itself. This is the control, this is the target because it is only simple phase gate. Okay. So that means, say on this one, I have applied this Z now. Whenever you are confused, so just remember the God is nothing but a matrix form of the circuit itself. So this is 1, 0, 0, 1, 0 minus 1. This is the gate, phase gate. It is applied on ket 1. ket1 क्या है? This one is the sorry, ket1 is 0, 0 and 1. So you just multiply it. So it should be a 2 cross 1 matrix only. So it's 1 into 0 plus 0 into 1. This is 0. And this is 0 into 0 plus minus 1 into 1, which is minus 1. That means minus ket1. Okay, now you have it. So your plus will be now minus and 1. And this one right now has no change in T2. Sorry, T2 to ye wala tha. T2 was this thing itself. Yes. Right now you are T3. So in T3 it will be 1 and 1. So T4 में क्या है? T4 में you have your control set where again this is control and second qubit is target. So this is first qubit which is a control and this one is a target. So it's half. If 0, no, nothing will happen. Minus, if this is 1, it will make this its phase to be minus 1. So both minus will come at front and it will be this thing. It might also happen that it is 1, 0. If it is 1, 0, then nothing will happen. That can happen after after some quantum gate. Maybe there is no operation based on the current state of the quantum. That can happen. Don't worry about that. So T4 is equals to 0, 0 plus 1, 1 again. Now, that is at T4. Okay, this is T3. This is T4. Last one is T5. But let us check. So T5 is, don't do anything. Just change the content of your qubit 1 and 2. Here we cannot see anything because if it would be 0, 1, I could have written here 1, 0 because here for both the cases values are 0, 0 and 1, 1 only. So it will be as it is and the final value will be ket 0, 0 plus ket 1, 1. If it is something, say 0, 1, it would be 1, 0. If it is 1, 0, it would be 0, 1. So that, but here it is being swapped, but you cannot, which day this problem solved? No, I am just taking a random circuit. So there was a day when I gave you a problem, but because of some interruption, we had to stop. And I told that on next day when I will start with that problem solve. But we start with a new concept. So I do not have any idea about that question because I dynamically created it at that time. That is why I asked that what are the basic gates that I used or showed to you. So these were all the gates like H, C naught, phase, C phase, swap, all these gates. Okay, I think now we are done. So I'm stopping my sharing. Okay. Still there are so many participants. In this case, swap gate is not doing anything, right? Swap gate is doing, but you are not seeing any result out of it because it is not clearly 0, 0, 1, 1 is the same thing only. That is what you are getting. Thank you, Mansi. Thank you. And happy Women's Day to all of you, those who are women here. Okay. So we will meet tomorrow. I guess you have exam post your class. First you have your exam. First you have your class. Then you have your 30-minute exam. So tomorrow I will try to keep it as like minimum as possible. That is why I know that none of you will be able to focus that much, and today's content was huge and this is very like rigorous. Absolutely understand it. So Thank you, Dr. Bhagu. Thank you so much. So what tomorrow we will be doing is we will actually put it little like less rigorous and look into the some of the hardware things. So I'll keep it fully kind of a theoretical one. No, no, no. Definitely, definitely no question will come from tomorrow's class. You have exam just after class. Okay. Thank you. Thank you. See you all tomorrow. Okay.